Welcome, friends. I'm so glad you're here, whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion. You found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the story of a visitor from another star, a frozen traveler that crossed an invisible line in space and suddenly came alive. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. On August 30th, 2019, in the hours before dawn, Gennady Borisov stands alone in the dome of the Margot Observatory on the Crimean Peninsula. The telescope tracks slowly across Cassiopeia, gathering photons from stars so distant their light has traveled for centuries. The CCD sensor integrates exposure after exposure, each image a thin slice of time pressed into pixels. Borisov has done this thousands of nights, searching for asteroids, for near-Earth objects, for anything that moves against the fixed cathedral of distant suns. The work is patient, the work is repetitive, the work asks for stillness. And then, in one frame, something moves. Not along the ecliptic plane where planets and asteroids flow, not in the gentle arc that gravity prescribes for objects bound to the sun. This motion cuts across the sky at an angle that does not belong. Borisov marks the position, waits, takes another exposure. The object has moved again, too far, too fast, too wrong. He measures the angular velocity, checks the coordinates against known catalogs. Nothing matches. The trajectory, even from these first few hours of observation, suggests something unprecedented. Only the second time in human history that this has happened. An object from interstellar space passing through our solar system while we watched. He submits the observation to the Minor Planet Center. Within hours, observatories across the planet turn their instruments toward the coordinates. The Hubble Space Telescope pivots in orbit. Ground-based spectrographs gather light and split it into rainbows of information. And in those first spectroscopic measurements, astronomers find water vapor, carbon monoxide, molecular signatures that confirm what the trajectory already whispered. This object formed elsewhere, around another star, in a stellar nursery we will never see. They name it C2019 Q4 Borisov in the official catalogs. But in those early days of September, before its interstellar nature is fully confirmed, it carries a provisional designation, 3I/Atlas. The I stands for interstellar, only the second ever catalogued, only the second visitor we have caught in the act of passing through. The orbit calculations come quickly now, refined with each new observation. Astronomers trace the path backward through space and forward into time. The numbers reveal a hyperbola, an open curve, unbound by the sun's gravity. This object did not originate here. It will not stay here. It is moving at 32 kilometers per second relative to the local standard of rest. The average motion of stars in our neighborhood of the galaxy, that velocity speaks of expulsion, of gravitational slingshots around distant planets, of a journey that began millions of years ago when something, perhaps a passing star, perhaps a giant planet's migration, ejected this frozen fragment from its home system and sent it wandering into the cold between. It approaches from the direction of Cassiopeia, from a region of sky where no particular star claims responsibility. Perhaps it came from a system now hundreds of light years displaced by the galaxy's rotation. Perhaps its parent star is a red dwarf, too dim to catalogue, too distant to notice. The origin remains uncertain. The trajectory, however, does not lie. Perihelion, closest approach to the Sun, will occur on December 8th, 2019. The object will pass 0 astronomical units from the solar surface, well outside Earth's orbit, never a threat, never close enough for detailed surface imaging, but close enough for spectroscopy, for thermal measurements, for observation of whatever transformations the sun's warmth might provoke, because comets, whether born here or elsewhere, obey the same physics. Ice sublimates when temperature rises above specific thresholds. Frozen gases, water, carbon monoxide, carbon dioxide, methane, each has its own vapor pressure curve, its own delicate relationship between temperature and phase, and distance from the sun determines temperature with mathematical precision. At 3.0 astronomical units from the sun, 3 times the distance from sun to Earth, a particular boundary exists. Not a physical surface, not a wall or membrane. Just a radius where the sun's radiant flux, spreading thinner with every meter of distance, drops below a critical threshold. At 3.0 AU, the equilibrium temperature of a dark, rotating body falls to approximately 150 Kelvin, and at 150 Kelvin, something happens to carbon monoxide ice. It begins to sublimate. Not dramatically, not explosively, just quietly, molecule by molecule. The frozen lattice releases its grip and the gas lifts away into vacuum. Sunlight pressure pushes it outward, creating the diffuse cloud called a coma. Radiation ionizes some fraction, and the solar wind sweeps those ions into a long, invisible tail. The comet becomes visible not as a point of light, but as a soft, glowing blur, the signature of outgassing, the mark of transformation. But in August, when Borisov first photographs the object, it lies beyond 3.0 astronomical units. The distance is 3.8 AU, and at that range, even carbon monoxide remains frozen. Water ice, which requires temperatures above 180 Kelvin to sublimate, stays locked solid. The nucleus is dormant. No coma, no tail, just a dark, frozen chunk of matter perhaps 400 meters across, tumbling silently through the inner solar system like a stone. Astronomers watch. They track the inbound trajectory, refining predictions, scheduling observation time on the world's most powerful instruments. They know what should happen. They know the boundary that waits ahead. They know that somewhere around 3.0 AU, the visitor will wake up. Only it took 4.5 billion years for this particular fragment to arrive here, and only a few weeks of inbound flight to reach the threshold. The observations accumulate in archives scattered across continents. Digital files stack in server farms, tagged with coordinates and timestamps. Each image captures a moment. Photons that left the sun, traveled to the comet, bounced off ice and dust, then traveled millions of kilometers more to strike silicon sensors on Earth. The light carries information encoded in wavelength and intensity. Spectrographs decode it. Computers process it. Scientists interpret it. And what they find in those early September days as 3I/Atlas crosses inward past 3.0 astronomical units is change. Sudden and unambiguous. The point source becomes diffuse. The spectroscopic lines shift and broaden. Carbon monoxide emission appears in the ultraviolet. The dormant visitor begins to outgas, not because it chose to, not because of any internal clock or biological imperative, simply because the sun's warmth reached the threshold where molecular bonds could no longer hold, and physics took over, patient and inevitable as always. The boundary is invisible, unmarked by any flag or monument, crossed in silence, but real nonetheless. As real as the phase diagrams that predict it, as real as the thermodynamic equations that govern every icy body in every stellar system across the galaxy. Somewhere in the archives, a specific image exists, taken perhaps on September 10th, perhaps September 11th, a frame that shows the comet not quite dormant, not quite active, caught in the very act of crossing. The first faint halo of coma barely detectable above background noise. This is the moment, this is the transformation. This is the thin boundary where 3I/Atlas changed behavior, and it will cross that boundary again, months later, on the outbound journey, only in reverse. The coma collapsing, the gases freezing, the silence returning. But that stillness lies ahead. For now. In September, the visitor warms, and the slow physics of sublimation writes its signature across the solar system in molecules of carbon monoxide, drifting outward toward the stars. The hyperbola does not curve like an ellipse. An ellipse returns, an ellipse closes upon itself, bound by gravity, sentenced to repetition. The planets trace ellipses. The comets of the Oort cloud, though flung to enormous distances, still follow ellipses so elongated they take millions of years to complete, but ellipses nonetheless, closed loops that bring them back. Eventually, always, a hyperbola opens. It arrives from infinity and departs toward infinity. It passes once and never returns. The mathematics are unambiguous. Orbital eccentricity greater than 1.0 means escape velocity has been exceeded. The object will not be captured. The sun's gravity bends the trajectory, curves it inward and then outward again, but cannot close the loop. The visitor swings past and continues outward, accelerating back toward interstellar speeds, receding until even the sun becomes just another star among stars. For 3I/Atlas, the orbital eccentricity calculates to 3.357, not barely unbound. Decisively unbound, hyperbolic beyond any measurement uncertainty. The trajectory stretches backward across light years and forward across light years, and this brief passage through the inner solar system occupies only the narrowest vertex of that cosmic arc. A moment of deflection in a journey measured in epochs. Astronomers trace the orbit backward, extrapolating motion through space and time. Galactic rotation complicates the calculation. Stars drift through the Milky Way in their own orbits around the galactic center, and over millions of years, the neighborhood rearranges itself. The sun moves, other stars move. The point of origin blurs, but the incoming trajectory suggests arrival from the direction of Cassiopeia, from a patch of sky with no obvious candidate star, no nearby system that might claim parentage. Perhaps the comet was ejected when its home star passed through a dense molecular cloud, gravitational perturbations scattering planetesimals into the void. Perhaps a giant planet migrated inward during the system's youth, flinging smaller bodies outward in the process, and this fragment happened to achieve escape velocity. Perhaps the parent star went supernova, though that seems unlikely. The comet shows no isotopic anomalies, no radionuclides that would mark proximity to stellar death. The truth is, we do not know where it came from, only that it came from elsewhere. The incoming velocity, measured relative to the local standard of rest, the average motion of nearby stars, is 32.2 kilometers per second. Not extraordinary by interstellar standards. Typical. In fact, for objects drifting through the galactic disk. Slow enough that the comet has likely been traveling for millions of years, crossing parsecs at speeds that seem fast on human scales, but glacial against the distances between stars. 3.8 astronomical units inbound, 3.0 astronomical units as the threshold. The distance narrows daily. The sun grows brighter in the comet's sky. Not that the comet has eyes to perceive brightness. Not that the frozen nucleus experiences anything resembling awareness, but the radiant flux increases according to the inverse square law, and temperature rises in response. And at some specific moment in early September, the surface temperature crosses 150 Kelvin. Carbon monoxide ice exists in a crystalline lattice at low temperatures, molecules locked in position by intermolecular forces. As temperature rises, the molecules vibrate more vigorously, At 150 Kelvin, the vibration energy equals the binding energy. The lattice begins to break apart. Molecules escape the surface and drift into vacuum. Sublimation has begun. Not melting. Comets do not melt in the way ice cubes melt in summer heat. The vacuum of space prevents liquid phase. Solid transitions directly to vapor, a process called sublimation, and the vapor expands outward into the near-perfect vacuum surrounding the nucleus. No air resistance, no atmospheric pressure to contain the expanding gas. Just molecules flying ballistically away from the surface, accelerated by their own thermal motion, spreading into a cloud that grows larger and more diffuse with every passing hour. The coma forms. Invisible at first, invisible light. Carbon monoxide does not scatter sunlight efficiently, but ultraviolet spectroscopy detects it. The Hubble Space Telescope, orbiting above Earth's atmosphere, points its cameras at the coordinates. The spectrograph splits incoming light into component wavelengths, and there, in the ultraviolet, the emission lines of carbon monoxide glow clearly. The comet is outgassing. The boundary has been crossed. On Earth, scientists examine the spectra. They measure line intensities, calculate outgassing rates, estimate the mass of gas being released per second. The numbers come back modest. This is not a vigorous comet by solar system standards. The outgassing rate is perhaps 1/10 that of a typical periodic comet at similar distance. The nucleus appears to be relatively inactive, or perhaps depleted of volatiles, or perhaps simply small. Early estimates suggest a diameter around 400 meters, though uncertainty remains large. Still, the transformation is undeniable. The dormant object has awakened. The frozen traveler has begun to evaporate. And here is the first irony. It took millions of years to arrive, and only days to change. Here is the second. The boundary that triggers the transformation is not unique to this comet, not special to interstellar visitors. Every comet obeys the same physics. Solar system comets cross the same threshold, sublimate the same ices, produce the same spectroscopic signatures. The only difference is that solar system comets cross it repeatedly, orbiting inward and outward in their ellipses, waking and sleeping on predictable schedules. 3I/Atlas crosses it twice, once inbound, once outbound, and then never again. Here is the third. We only discovered interstellar objects recently, but they have been passing through the solar system for all of Earth's history. Millions of them, perhaps billions. We just never saw them before. We didn't have the telescopes. We did not have the automated sky surveys. We did not have the computational power to detect faint, fast-moving objects against the stellar background and calculate their orbits quickly enough to identify the hyperbolic trajectories before the visitors departed beyond observation range. In 2017, Oumuamua became the first confirmed interstellar object. In 2019, 3I/Atlas became the second, and now we know they are common. Now we know the galaxy is full of wanderers, fragments ejected from planetary systems across hundreds of billions of stars, drifting through the void, occasionally passing close enough to another star to be warmed briefly before continuing into darkness. The carbon monoxide emission strengthens through September. Observatories in Chile, Hawaii, Spain, and California gather data. Radio telescopes search for molecular lines. Infrared instruments measure thermal emission from the nucleus. Slowly, a picture emerges. This is a small comet, primitive, rich in carbon monoxide relative to water, unusual compared to solar system comets, which tend to be water-dominated. The carbon monoxide abundance suggests formation in a colder environment, farther from its parent star, where CO ice could condense alongside water ice instead of being lost to early sublimation. The chemistry whispers clues about the distant stellar nursery where this object formed. A system colder than ours, perhaps, or a formation zone farther from the star, in regions analogous to our Kuiper belt or Oort cloud. The exact ratios of volatiles, carbon monoxide to water, carbon dioxide to methane, encode information about temperature and pressure conditions during the comet's birth. 4.5 billion years ago, in a place we will never visit and cannot name. And yet, the physics that governs its behavior here, now, in our solar system, is universal. The same equations describe sublimation, whether the ice formed around Alpha Centauri or around the Sun. The same thermodynamic principles apply. The boundary at 3.0 astronomical units would exist for any comet approaching any star of roughly solar luminosity. The distance might shift slightly for hotter or cooler stars, but the principle remains. There is always a threshold where warmth exceeds bonding energy, where solid becomes vapor, where the dormant awakens. Only took crossing half the galaxy to reach it. Only took humanity 4 billion years to witness the crossing. Only took a Crimean astronomer standing alone in the pre-dawn cold to notice something moving wrong. Spectroscopy is the art of reading light, not the brightness, but the color, or more precisely, the exact wavelengths present and absent in the electromagnetic spectrum. Every element, every molecule, every chemical bond absorbs and emits light at specific frequencies determined by quantum mechanics. Hydrogen produces one pattern, oxygen another, carbon monoxide another still. The patterns are as distinct as fingerprints, as reliable as mathematics. When sunlight strikes the nucleus of 3I/Atlas, some photons reflect unchanged, others are absorbed by molecules in the coma, the expanding cloud of gas surrounding the nucleus. The absorbed energy excites electrons to higher energy states. Milliseconds later, the electrons fall back to lower states, releasing photons at specific wavelengths. These emission lines appear in the spectrum as bright spikes against the background continuum. By measuring which lines appear and how bright they are, astronomers can identify which molecules are present and estimate their abundances. The first detailed spectra come from the William Herschel telescope on La Palma in the Canary Islands. The spectrograph splits incoming light into a rainbow spread across thousands of detector pixels. Computer algorithms identify emission lines, match them to known molecular transitions, calculate intensities. The results appear on screens in observatory control rooms within hours of observation. Carbon monoxide, present, strong emission in ultraviolet wavelengths, weaker in visible light. The CO molecule rotates and vibrates, each motion corresponding to specific energy levels, each transition producing characteristic photon wavelengths. The pattern is unmistakable. Water, present but weak. The H2O lines appear fainter than expected. The ratio of carbon monoxide to water is unusually high, perhaps 3:1. Compared to typical ratios near 1:10 for solar system comets, this difference matters. It suggests the comet formed in a region where carbon monoxide could condense efficiently, implying temperatures below 25 Kelvin during formation. Our solar system's comets likely formed at slightly warmer temperatures where water ice dominated and much of the carbon monoxide remained gaseous and was lost. Cyanogen, absent. This surprises observers. CN, a molecule of one carbon and one nitrogen, appears prominently in nearly every solar system comet spectrum. It forms from photodissociation of more complex organic molecules in the coma, and its distinctive violet emission makes it easy to detect. But in 3I/Atlas, the CN lines are missing, or at least far weaker than expected. The comet shows no significant cyanogen emission. The absence speaks volumes. Either the comet is depleted in nitrogen-bearing organics, or the chemistry that produces CN in solar system comets does not operate efficiently here. Perhaps the parent molecules are different. Perhaps the formation conditions in the alien stellar system produced a different mix of ices and refractories. The missing cyanogen becomes one of the comet's defining characteristics, evidence that not all comets are chemically identical. That formation environment matters, that this visitor carries the signature of elsewhere in its very composition. Dust is also present, though sparse. The nucleus sheds small particles along with gas, microscopic grains of silicate and carbonaceous material, the solid remnants of the protoplanetary disk where the comet formed. These grains scatter sunlight, producing a faint dust tail that extends in the direction opposite the sun. The tail is subtle, barely detectable in long-exposure images, far less prominent than the dust tails of active solar system comets. This suggests either a low dust-to-gas ratio or simply low overall activity. The comet is not vigorous. It outgasses reluctantly, as if its ices are bound more tightly than expected, or perhaps already partially depleted by some previous close encounter with a star during its millions of years of wandering. The nucleus itself remains difficult to observe. At peak brightness, 3I/Atlas reaches apparent magnitude 15, far too faint for naked eye visibility, requiring telescopes of moderate size even to detect. The coma obscures the nucleus in visible light, making direct imaging of the solid body nearly impossible. Astronomers estimate size from thermal emission in the infrared, assuming a particular albedo, the fraction of sunlight reflected rather than absorbed. Albedos of comets vary widely, from 4% to 15%, and without direct measurement. The size estimate carries large uncertainty. The best models suggest a nucleus approximately 400 meters in diameter, not large, smaller than many near-Earth asteroids, a dark, irregularly shaped body tumbling through space, spinning at some unknown rate. Its surface a mixture of ancient ice and carbonaceous dust that has never seen sunlight until now, or more precisely, never saw sunlight from our sun, though it must have been illuminated by its parent star billions of years ago. Before ejection. Before the long voyage through interstellar darkness, rotation period measurements come from photometry, repeated brightness measurements over time. As the nucleus spins, different surface areas face Earth and Sun. If the shape is irregular or the albedo patchy, the brightness varies periodically. Observers measure the brightness every few minutes across multiple nights, searching for periodic signals in the light curve. The data show variability, but the period is not immediately obvious. The amplitude is small, perhaps 0, 1 magnitudes, suggesting either a nearly spherical shape or an axis of rotation pointing roughly toward Earth. Further observations through October and November refine the estimate. The rotation period appears to be approximately 7 to 8 hours. Though uncertainty remains, the nucleus is likely elongated, perhaps twice as long as it is wide, tumbling slowly as it travels. This tumbling motion is itself a relic of the comet's violent history. The spin was imparted by some ancient collision or gravitational interaction, perhaps during the ejection event that sent the comet into interstellar space, perhaps even earlier during the chaotic formation of its home planetary system. Angular momentum is conserved in the vacuum of space, so the spin continues unchanged across millions of years, a memory of forces long since dissipated, a reminder that nothing in space is truly still. The warming continues through September and into October. The comet approaches closer to the Sun, crossing 2.5 astronomical units, then 2.0 AU. Temperature rises. Water ice begins to sublimate alongside carbon monoxide. The outgassing rate increases. The coma expands. By mid-October, the coma diameter reaches 100,000 kilometers, larger than Jupiter, though far more diffuse. With density so low that the entire visible cloud contains only a few kilograms of gas spread across an enormous volume, Observers note that the comet's activity level increases approximately with the inverse square of solar distance, as expected from the inverse square law of radiation. This suggests sublimation is driven primarily by direct solar heating of the surface, rather than internal heat or other exotic mechanisms. The physics is straightforward. The sun warms the nucleus. The ice sublimates. The gas escapes. The process is as simple as evaporation, only in vacuum and at temperatures hundreds of degrees below freezing. And yet, mysteries remain. The exact composition of the nucleus is unknown. The internal structure, whether it is a solid monolith or a rubble pile of smaller fragments, cannot be determined from available observations. The comet's exact age, the identity of its parent star, the circumstances of its ejection, the details of its journey across light years, all remain uncertain, perhaps unknowable. What is known is this: somewhere around September 10th, 2019, plus or minus a day. The surface temperature of the nucleus crossed 150 Kelvin as the comet passed inward through 3.0 astronomical units from the Sun. Carbon monoxide ice began to sublimate. The dormant object began to outgas. The transformation was detected by telescopes on Earth within days. The boundary was crossed, and nothing would be the same. Except, of course, that everything remained the same. The comet continued inbound along its hyperbolic trajectory. The laws of physics continued to operate without deviation. The universe proceeded exactly as it had before, indifferent to whether humans happened to notice this particular crossing of this particular threshold by this particular visitor from another star. Only we noticed. Only we measured. Only we assigned meaning to the transformation. The comet itself, insensate and ancient, simply continued to sublimate. 3 astronomical units is not a place. It is a distance, a radius. A sphere expanding outward from the Sun at 450 million kilometers, invisible and intangible, marked by nothing except mathematics and consequence. No particle occupies that boundary specifically. No force field hums at that distance. The vacuum there is indistinguishable from the vacuum slightly closer or slightly farther. Space at 3.0 AU looks exactly like space at 2.9 AU or 3, 1 AU, black, empty, scattered with starlight, permeated by the solar wind's thin plasma and the sun's declining magnetic field. And yet, the boundary is real. Temperature is real. Thermodynamics is real. At 3.0 AU from a G-type star of solar luminosity, a dark body in thermal equilibrium reaches approximately 150 Kelvin. This is not arbitrary. This is not approximate. This is deterministic, calculable from first principles, following directly from the Stefan-Boltzmann law and the inverse square law of radiation. The Sun radiates energy at a rate of 3.828 x 1026 watts. This energy spreads outward in all directions, diluting with the square of distance. At 1.0 AU, Earth's distance, the solar flux is 1361 watts per square meter. At 3.0 AU, the flux is 1/9 of that, 151 watts per square meter. A dark body absorbing this radiation and re-radiating it as thermal infrared reaches equilibrium when absorbed power equals emitted power. The equilibrium temperature depends on albedo and emissivity, but for a typical dark comet with low reflectivity, the surface temperature at 3.0 AU calculates to 150 Kelvin, give or take a few degrees depending on exact assumptions. 150 Kelvin is cold by human standards, negative 123 degrees Celsius, negative 190 degrees Fahrenheit, colder than any winter on Earth, colder than the polar ice caps of Mars, colder than the surface of Titan, but not as cold as the outer solar system, not as cold as Pluto's surface at 40 Kelvin, not as cold as interstellar space at 2.7 Kelvin. the cosmic microwave background temperature left over from the Big Bang. At 150 Kelvin, carbon monoxide ice becomes unstable. The vapor pressure of CO ice at this temperature is approximately 10 to 6 millibars, a trillionth of Earth's atmospheric pressure, but infinitely larger than the vacuum of space. When vapor pressure exceeds ambient pressure, sublimation occurs. The solid phase cannot persist. Molecules escape the surface and fly away into vacuum, never to return. Water ice, by contrast, remains stable at 150 Kelvin. The vapor pressure of H2O ice at this temperature is negligible, perhaps 10-12 millibars. Water sublimation does not become significant until temperatures rise above 180 Kelvin, which occurs around 2.5 AU for a typical comet, closer to the Sun. Water dominates the outgassing. Farther out, carbon monoxide dominates. At intermediate distances, both contribute. This is why comets change character with distance. This is why different volatiles activate at different heliocentric distances. This is why the appearance and composition of a coma evolve as the comet travels inward and outward along its orbit. The Sun provides a temperature gradient, and chemistry responds. For 3I/Atlas, the carbon monoxide activation distance is especially important because the comet appears to be CO-rich relative to water. The 3.0 AU boundary marks the moment when the comet's most abundant volatile begins to sublimate vigorously. This is the transformation point. This is where dormancy ends and activity begins. The exact location of the boundary depends on factors beyond simple distance. The comet's rotation affects surface temperature. Sunlit areas heat up, shadowed areas cool down, and the average temperature depends on rotation period and axis orientation. The comet's thermal inertia matters, how quickly the surface responds to changing solar illumination. High thermal inertia means the surface stays warmer in shadow and cooler in sunlight, smoothing out temperature variations. Low thermal inertia means rapid heating and cooling, with larger temperature swings between day and night. The nucleus shape affects temperature distribution. An elongated, tumbling body presents different surface areas to the Sun at different times. Craters and crevices trap shadows. Slopes face the Sun at varying angles, receiving different amounts of radiation per unit area. The surface is not isothermal. Some regions may cross the sublimation threshold before others, creating localized jets of outgassing from active areas, while other parts of the nucleus remain dormant. Dust covering the surface can insulate underlying ice, raising the threshold distance for sublimation. A thick dust mantle may prevent outgassing entirely, creating a dormant comet that appears asteroidal despite being ice-rich beneath the surface. Conversely, freshly exposed ice sublimates readily, creating vigorous outgassing from small active areas. The comet's history of previous heating events, if it passed near other stars during its interstellar journey, might have depleted surface volatiles, leaving only deeper ice that requires higher temperatures to sublimate. All these complications exist. All these factors influence the exact distance where sublimation begins. And yet, to first order, the boundary is 3.0 AU for carbon monoxide, 2.5 AU for water. These numbers appear in textbooks. These numbers guide mission planning. These numbers summarize billions of years of cometary evolution across countless stellar systems. The boundary is invisible but empirical. We know it exists because we observe comets crossing it. We watch dormant nuclei develop comae. We measure the onset of molecular emission in spectra. We track outgassing rates as functions of distance. The data confirm the theory. The theory predicts new observations. The cycle continues. For 3I/Atlas, the crossing happens in early September 2019. The comet approaches from 3.8 AU inbound each day. The distance decreases by approximately 0.028 each day. The temperature rises by a fraction of a degree. On September 9th, the comet is at 3.02 AU, surface temperature 149 Kelvin, carbon monoxide sublimation barely detectable. On September 10th, the comet is at 3.00 AU, temperature 150 Kelvin, sublimation ramping up. On September 11th, distance 2.98 AU, temperature 151 Kelvin. The coma now clearly visible in ultraviolet observations. The transition is not instantaneous. Sublimation increases gradually over several days as temperature rises through the critical range. But the change is rapid compared to the comet's overall journey. After millions of years of dormancy in interstellar space, the transformation from inactive to active occupies less than a week. Observers on Earth watch the process in real time, or as close to real time as light speed delay allows. Photons leaving the comet travel for 20 to 30 minutes before reaching Earth. Telescopes capture them. Detectors convert them to electrical signals. Computers process the signals. Scientists interpret the results. The entire chain from photon emission to human understanding takes hours at most. And what humans understand is this: the boundary is not special to this comet. It is not unique to interstellar visitors. It is a universal feature of cometary physics, operating the same way for every icy body approaching every star of similar luminosity. The Sun does not know this comet came from elsewhere. The physics does not care about the comet's origin. The boundary applies equally to all. Only we care about the origin. Only we marvel at the visitor from another star. Only we assign significance to this particular crossing of this particular threshold. The universe simply continues its calculations, solving differential equations of heat transfer and molecular dynamics, processing inputs and producing outputs, indifferent to whether any conscious observer happens to notice. The temperature rises, the ice sublimates, the boundary is crossed, consequences follow automatically. In August, before the crossing, 3I/Atlas moves inward through the outer solar system in silence. No coma surrounds the nucleus, no tail streams behind it. The object appears point-like in telescope images, a single pixel of reflected sunlight moving against the stellar background. Spectroscopy shows only reflected solar spectrum. The continuous rainbow of sunlight bouncing off the surface without modification. No emission lines, no molecular signatures, just reflected light, faint and cold. The surface temperature at 3.8 AU calculates to approximately 135 Kelvin. Too cold for carbon monoxide sublimation, far too cold for water. The nucleus is frozen solid. Its surface a mixture of ancient ices and dark carbonaceous material that has been cold for millions of years. The last time this object was warm, truly warm enough for vigorous sublimation, was presumably before its ejection from its home system, when it orbited closer to its parent star. Since then, only the faint warmth of starlight in interstellar space, enough to maintain temperatures around 10 to 20 Kelvin, depending on the density of nearby stars. In interstellar space, the comet would have been cold enough for nearly everything to freeze. Not just water and carbon monoxide, but also nitrogen, methane, even argon and neon at sufficient depth or in sufficiently shadowed regions. The surface would have been dominated by the most refractory ices, those that sublimate at the lowest temperatures. Water ice would have formed a solid matrix. Volatile gases would have been trapped within, but space is not empty, even between stars. A tenuous medium exists, the interstellar medium, primarily hydrogen and helium gas at densities around 1 atom per cubic centimeter. Energetic cosmic rays, high-speed protons and atomic nuclei accelerated by supernova shockwaves and other violent events, permeate this medium. These cosmic rays strike any object they encounter, depositing energy, ionizing molecules, breaking chemical bonds. Over millions of years, Cosmic ray exposure alters the surface chemistry of interstellar objects. Organic molecules are destroyed or rearranged. Ice structure changes. New compounds form from radiolysis, radiation-induced chemistry. The surface darkens as complex organics polymerize into refractory carbon compounds. The comet's surface, when it finally enters our solar system, carries the chemical signature of this long exposure, a record of its journey through the galaxy written in isotopic ratios and molecular abundances. The incoming trajectory brings the comet past the orbit of Jupiter, past the asteroid belt, inward toward the inner solar system. At each stage of the journey, the sun grows brighter in the comet's sky. At 5.0 AUA, the sun subtends an angular diameter of about 4 arcminutes, 10 times smaller than viewed from Earth. At 4.0 AU, the sun is slightly larger, slightly brighter. At 3.5 AU, the solar disk measures 8 arcminutes across, and the radiation flux begins to approach levels sufficient for significant heating, but still no outgassing. Not yet. The surface temperature at 3.5 AU is 140 Kelvin, below the threshold. Carbon monoxide ice remains stable. Water ice remains deeply frozen. The comet continues inward as a dormant body, inert and silent, giving no visible indication that it is anything other than a distant asteroid. Observers on Earth continue tracking it. Astrometric measurements refine the orbit. Every positional measurement improves the trajectory calculation, reduces uncertainty in perihelion distance and timing. The orbit is now known precisely enough to predict the comet's location years into the future, or at least until it passes beyond the range of detection. Billions of kilometers from the Sun, heading back out into the galaxy. Photometric observations measure brightness variations. The comet's apparent magnitude is approximately 17.5 in late August, visible only in large amateur telescopes and professional instruments. The brightness changes slightly from night to night, perhaps indicating rotation, perhaps just noise in the measurements. The signal is weak. The comet is small and distant. Every photon captured is precious. Spectroscopic observations continue as well. Though the faint target makes spectroscopy challenging, long exposures are required to gather enough light. The spectra show only the reflected solar continuum, the sun's light, redder than normal due to the comet's reddish surface, but otherwise unmodified. No emission lines, no absorption features beyond what the sun itself produces. The spectrum of a dormant comet is essentially featureless, revealing nothing about composition or activity. And then, as September begins, the comet crosses 3.2 AU. Temperature 148 Kelvin. Still below threshold, but approaching. The surface is warming. Molecules in the ice lattice vibrate more vigorously. Bonds strain but do not yet break. The sublimation rate is negligible. Perhaps a few molecules per square meter per second escaping from the warmest sunlit surfaces. Not enough to create a detectable coma. Not enough to register in any observation. September 5th. Distance 3.1 AU. Temperature 149 Kelvin. The sublimation rate increases. Carbon monoxide molecules begin leaving the surface in greater numbers, escaping into vacuum. Flying away at thermal velocities of several hundred meters per second, but the outgassing is still weak. The coma, if it exists at all, is too faint to detect. September 8th. Distance 3.02 A1A. Temperature 149.5 Kelvin. The boundary is very close now. Sublimation accelerates exponentially with temperature. The vapor pressure curve is steep in this range. A change of 1 or 2 degrees can increase sublimation rate by a factor of 10. The comet is approaching the critical transition. September 10th. Distance 3.0 AU. Temperature 150 Kelvin. The threshold, the boundary. the invisible radius where equilibrium tips from dormancy to activity, somewhere on the nucleus, perhaps at the subsolar point where the sun's rays strike most directly. The surface temperature crosses 150 Kelvin. Carbon monoxide begins sublimating vigorously. Gas streams away from the surface. The coma begins to form. But the transformation is not dramatic. There is no explosive outburst, no sudden eruption, just a gradual increase in outgassing rate as temperature rises through the critical range. The physics is continuous. The change is smooth. Only in retrospect does the crossing appear as a distinct event, a before and after, separated by this invisible boundary. Ultraviolet observations on September 11th detect carbon monoxide emission for the first time. The lines are weak but unambiguous. The comet is outgassing. The dormant visitor has awakened. The boundary has been crossed. Observers exchange emails, post updates to astronomical telegram services, schedule follow-up observations. The transition is scientifically significant. This is only the second interstellar comet ever observed, and the first for which the activation has been caught in near real time. The data will constrain models of cometary composition and activity. The observations will guide planning for future encounters with interstellar objects. But for the comet itself, nothing has changed except temperature. The same object follows the same trajectory. The same ices sublimate according to the same physics. The same sunlight drives the same processes. The universe continues its calculations, processing the differential equations of thermodynamics and orbital mechanics, advancing time step by step, indifferent to human observation. Only we mark the moment. Only we record the transformation. Only we assign meaning to the crossing. The comet, ancient and insensate, simply warms and sublimates, doing what comets have done around billions of stars across billions of years. Only this time, someone was watching. Sublimation is escape, molecule by molecule. The solid phase disintegrates. The process is not melting, there is no liquid intermediate. In vacuum at low pressure, ice transitions directly from solid to vapor, skipping the liquid phase entirely. The phase diagram of water or carbon monoxide shows this clearly. Below a certain pressure, the liquid region vanishes, and the boundary between solid and vapor becomes the only transition that matters. On Earth, ice melts because atmospheric pressure stabilizes liquid water. On a comet nucleus, no atmosphere exists. Pressure at the surface is effectively zero, dominated by the vapor pressure of sublimating ice itself, which is far too low to sustain liquid phase. So the ice sublimes. Molecules gain enough thermal energy to break free from the crystal lattice and fly away into space as gas. The energy required for sublimation is called the latent heat of sublimation. For water ice, this is about 2.8 million joules per kilogram. For carbon monoxide ice, approximately 380,000 joules per kilogram. This energy must be supplied by sunlight. Solar radiation heats the surface, and that heat energy breaks molecular bonds, allowing molecules to escape. Each molecule that escapes carries away energy, cooling the surface in a process analogous to evaporative cooling, the same physics that makes sweat cool human skin, only operating at temperatures hundreds of degrees colder. The sublimation rate depends on temperature through the Clausius-Clapeyron equation, which relates vapor pressure to temperature. The relationship is exponential. Small increases in temperature produce large increases in sublimation rate. At 140 Kelvin, carbon monoxide sublimation is negligible. At 150 Kelvin, it is significant. At 160 Kelvin, it is vigorous. A 10-degree temperature change can increase the sublimation rate by a factor of 100. This exponential dependence creates a sharp threshold effect. As the comet approaches, the sun and surface temperature rises. Sublimation accelerates rapidly over a narrow distance range. The transition from dormant to active appears sudden. Even though the underlying physics is continuous, the boundary at 3.0 AU is not a discontinuity in the equations, just the distance where the exponential curve crosses from negligible to significant. For 3I/Atlas, the crossing happens in early September. The surface warms through 150 Kelvin. Carbon monoxide molecules in the ice lattice vibrate energetically. Bonds break. Molecules escape. The sublimation rate climbs from near zero to approximately 1,020 molecules per second, 100 billion molecules every second, leaving the surface and expanding into the surrounding vacuum. This sounds like a large number, and in absolute terms it is, but the comet nucleus is approximately 400 meters across, with a surface area around 500,000 square meters. The sublimation rate per unit area is only about 10-14 molecules per square meter per second. Each square meter loses 100 trillion molecules every second. This is intense by human standards, but modest by cometary standards, about 1/10 the sublimation rate of a typical solar system comet at similar distance. The escaping molecules travel ballistically. Thermal velocity of carbon monoxide at 150 Kelvin is approximately 200 meters per second, the speed at which molecules move randomly due to thermal motion. This is the escape velocity from the nucleus as well. Given the tiny gravity of such a small body, any molecule that leaves the surface escapes permanently. No atmosphere forms. No bound envelope of gas surrounds the nucleus. The molecules simply fly away in straight lines, creating an expanding cloud that grows larger and more diffuse with time. This expanding cloud is the coma. At first, immediately after crossing the threshold, the coma is small and faint, only a few thousand kilometers across, containing only a few grams of gas. But as outgassing continues, the coma grows. By mid-September, the coma diameter reaches 10,000 kilometers. By late September, 50,000 kilometers. By October, over 100,000 kilometers, larger than Jupiter, though incomparably less dense. The coma is not uniform. Near the nucleus, gas density is relatively high, perhaps 106 molecules per cubic centimeter. Farther out, density falls with the square of distance from the nucleus. At the outer edge of the coma, density is perhaps 102 molecules per cubic centimeter, still millions of times denser than interstellar space, but far more tenuous than the best laboratory vacuum achievable on Earth. The coma is, by any human standard, empty space, and yet it glows in ultraviolet light visible to sensitive instruments, detectable across millions of kilometers. The glow comes from fluorescence. Sunlight strikes carbon monoxide molecules in the coma. Ultraviolet photons from the sun have enough energy to excite electrons in the molecules to higher energy states. The molecules absorb these photons, then re-emit photons at specific wavelengths as electrons fall back to lower states. This re-emission produces the characteristic spectral lines that identify carbon monoxide in the coma. The process is inefficient. Most molecules in the coma do not fluoresce at any given moment. The gas is so tenuous that collisions between molecules are rare. Each molecule exists in effective isolation, absorbing and emitting photons independently. But there are enough molecules, 10^28 or more in the entire coma, that the collective glow is detectable. Sunlight pressure also affects the coma. Photons carry momentum, and when they are absorbed or scattered by molecules, that momentum is transferred. The force is tiny, only a few piconewtons per molecule, but it acts continuously, pushing molecules away from the sun. Over time, this pressure accelerates molecules outward, creating a tail that extends in the anti-solar direction. For 3I/Atlas, the tail is primarily a gas tail, carbon monoxide molecules pushed by radiation pressure. Dust is also present, shedding from the nucleus along with gas, but the dust production rate appears low. The dust tail is faint, barely visible in long exposure images. The comet is not dusty. Perhaps the nucleus has a low dust content. Perhaps the dust is bound tightly into the ice matrix and does not release easily during sublimation. The tail grows as the comet approaches the Sun. By October, the tail extends several 100,000 kilometers. By November, over 1,000,000 kilometers. The tail is not solid. It is not even continuous. It is a stream of individual molecules, each following its own ballistic trajectory under the combined influence of solar gravity, radiation pressure, and solar wind. The tail is ephemeral, regenerated constantly by ongoing sublimation, dispersing slowly into interplanetary space. And all of this, the coma, the tail, the fluorescence, the outgassing, begins at the boundary, begins when temperature crosses the threshold, begins when the sun's warmth exceeds the binding energy of ice. The physics is deterministic. Given the comet's trajectory and the sun's luminosity, the activation distance can be calculated in advance. The transformation is predictable. Only the exact details remain uncertain. The sublimation rate depends on surface composition, dust coverage, rotation, shape. The coma structure depends on gas velocity, expansion rate, photodissociation timescales. The tail morphology depends on dust properties, radiation pressure efficiency, solar wind conditions. These details vary from comet to comet, even among solar system comets. And they vary even more for interstellar visitors with unknown formation histories. But the threshold itself is universal. 3 astronomical units for carbon monoxide, 2.5 for water. The boundary exists for every comet approaching every sun-like star. Only took the universe 8 billion years to create the physics. Only took this comet a few million years to reach the boundary. Only took humanity a few days to measure the crossing. September progresses. The comet continues inward. Distance decreases daily. Temperature rises. Sublimation accelerates. What began as a faint detection in ultraviolet spectroscopy becomes unambiguous. The carbon monoxide emission lines strengthen. The coma expands. The comet is fully active now, outgassing steadily as it approaches perihelion. By September 20th, the comet has crossed 2.7 AU inbound. Surface temperature reaches 155 Kelvin. The carbon monoxide sublimation rate has increased by a factor of 5 compared to the initial activation. The coma diameter exceeds 40,000 kilometers. Photometric measurements show the comet has brightened to magnitude 16. 5, still far too faint for amateur observation, but easily detectable with moderate professional telescopes. Spectroscopic observations multiply. Observatories around the world contribute data. The Keck telescopes in Hawaii, the Very Large Telescope in Chile, the Gran Telescopio Canarias in Spain. Each instrument brings unique capabilities. High-resolution spectrographs reveal fine structure in emission lines. Infrared spectrometers detect thermal emission from the nucleus. Ultraviolet instruments measure emission from excited molecular states. The carbon monoxide lines dominate the spectrum. The CO molecule has a simple electronic structure, and its spectroscopic signatures are well understood. The emission appears primarily in the ultraviolet, from transitions between vibrational and rotational energy levels. By measuring the line intensities and profiles, astronomers calculate the outgassing rate, the gas temperature, the velocity distribution in the coma. Water emission also appears, though weaker. As temperature rises above 150 Kelvin, water ice begins to sublimate alongside carbon monoxide. The H2O lines appear in infrared spectra, and the hydroxyl radical OH, produced when ultraviolet sunlight breaks apart water molecules, shows up in ultraviolet observations. but the water production rate is only about 1/3 that of carbon monoxide, confirming the unusual CO-rich composition of this interstellar visitor. The ratio of carbon monoxide to water is approximately 3, 1 by mass, or about 2, 1 by number of molecules. This is highly unusual. Solar system comets typically show CO-H2O ratios around 0.1 or less. Water dominates by a factor of 10. Only a few solar system comets show elevated carbon monoxide, and even those rarely exceed ratios of 1. The 3I/Atlas ratio of 3. 1 is extreme, suggesting formation conditions very different from the solar nebula. The implication is clear. This comet formed in a colder region of its home protoplanetary disk, or around a cooler star, where carbon monoxide could condense efficiently without being overwhelmed by water ice. The exact temperature required depends on pressure and gas phase abundances, but models suggest formation temperatures below 25 Kelvin, compared to typical formation temperatures around 30, 40 Kelvin for solar system comets, a difference of 10 or 15 degrees. Billions of years ago, preserved in the ice composition, readable now through spectroscopy. The comet carries chemical memory of its birthplace, encoded in the ratio of volatile molecules, decoded by light. The missing cyanogen remains puzzling. By late September, with the comet fully active and producing significant amounts of gas, the CN emission should be strong. In solar system comets, cyanogen is ubiquitous. It forms from photodissociation of HCN, hydrogen cyanide, and other nitrogen-bearing organics. The violet CN bands appear prominently in every comet spectrum, but not in 3I/Atlas. The CN emission is weak or absent. Searches for other nitrogen-bearing species, N2, NH3, HCN, also come back negative or marginal. The comet appears depleted in nitrogen compounds, or at least in the volatile nitrogen species that produce observable emission. This depletion is another chemical signature of the alien formation environment. Perhaps the protoplanetary disk around the parent star was nitrogen poor. Perhaps nitrogen was locked into refractory compounds that do not sublimate readily. Perhaps the formation zone was so cold that nitrogen condensed as N2 ice and has been lost or is trapped deep beneath the surface. The exact explanation remains uncertain. Different formation scenarios produce different predictions. Distinguishing between them would require more detailed observations, isotopic measurements, detection of minor species, measurement of other elemental ratios. But 3I/Atlas is small and faint. The signal is weak. The comet is observable for only a few months before it recedes beyond detection range. Some questions will remain unanswered. By October 1st, the comet crosses 2.5 AU inbound. Temperature reaches 162 Kelvin. Water sublimation is now vigorous, contributing significantly to the total outgassing. The coma diameter exceeds 80,000 kilometers. The dust tail becomes more prominent, though still faint. A subtle fan of scattered sunlight extending away from the nucleus in the anti-solar direction. Observers note that the dust tail shows some structure, not a smooth, continuous fan, but subtle streamers and filaments, suggesting episodic dust ejection or variation in outgassing rate across the nucleus surface. Perhaps the rotation exposes different regions to sunlight at different times, creating periodic pulses of activity. Perhaps localized jets are active on the sunlit hemisphere. High-resolution images might reveal these features, but 3I/Atlas remains too distant and faint for detailed imaging. The structure is barely detectable, hints of complexity in the otherwise featureless glow. The outgassing rate continues to increase as the comet approaches perihelion. Models predict peak activity in early December when the comet passes closest to the Sun, but even at peak, the activity level is expected to be modest. perhaps 1/10 that of a typical solar system comet at similar distance. The nucleus is small. The volatile content, though high in carbon monoxide, may be limited in total mass. The comet is not destined for spectacular displays. It will remain a telescopic object throughout its passage, never becoming bright enough for naked eye visibility. And this, too, is scientifically valuable. Not all comets are spectacular. Not all visitors announce themselves with brilliant tales and dramatic outbursts. Most comets are small, faint, ordinary, at least in appearance. Their value lies not in visual splendor, but in the information they carry, the chemical signatures they preserve, the physics they demonstrate. 3I/Atlas is ordinary in its physics. The sublimation follows standard models. The outgassing rate scales predictably with distance and temperature. The coma structure matches theoretical expectations. The trajectory conforms precisely to Newtonian mechanics, following the hyperbolic orbit calculated from position measurements with zero deviation. And yet the comet is extraordinary in origin. It came from another star. It formed in another planetary system. It carries chemistry from another stellar environment. Every measurement, every spectrum, every observation adds to the sparse catalogue of interstellar objects. Building statistical samples, testing theories of planet formation and system evolution across the galaxy. Only 2 confirmed interstellar objects by late 2019, Oumuamua in 2017, and now 3I/Atlas. 2 examples from which to draw conclusions about populations, compositions, ejection mechanisms. The statistics are weak. The uncertainty is large. But the observations continue. Sky surveys improve. Detection capabilities increase. Future visitors will be caught and characterized. The sample will grow. For now. In October 2019, observers focus on 3I/Atlas. Telescopes track the comet nightly. Spectra accumulate in archives. Photometric data points march across light curves. The transformation that began at 3.0 AU continues, driven by steadily rising temperature, approaching the peak that will come at perihelion in December. The boundary has been crossed. The dormant object has awakened. The physics proceeds automatically. Differential equations solving themselves in real time, producing outcomes determined by initial conditions and natural law. Molecules sublimate, gas expands, light scatters, spectrographs measure, computers record, scientists interpret. And somewhere in the data, buried in the numbers and spectra and images, lies the chemical signature of elsewhere, the faint echo of a stellar system we will never visit, preserved in ice ratios and missing molecules, readable to those who know how to look. The comet does not know it carries this information. The ice does not remember its origin. The molecules sublimate blindly. Following physics without purpose or meaning, only we assign meaning, only we read the signatures. Only we reconstruct the story. The universe simply continues its calculations, processing the thermodynamics of sublimation, the mechanics of orbital motion, the quantum physics of fluorescence. Indifferent to interpretation, the comet warms, the ice sublimates, the transformation continues. Cyanogen is CN, 1 carbon bonded to 1 nitrogen. The bond is strong, a triple bond, among the strongest in molecular chemistry. The molecule is stable, persistent, difficult to break apart once formed. And yet it is toxic, reactive, a product of high-temperature chemistry and photochemical processes. In comet comet, cyanogen appears not from the ice itself, but from parent molecules, larger, more complex organics that contain carbon and nitrogen in various combinations. Hydrogen cyanide. HCN is the primary parent. It sublimates from the nucleus along with water and carbon monoxide, then drifts into the coma where ultraviolet sunlight breaks it apart. The photodissociation process splits HCN into hydrogen and CN. The cyanogen radical fluoresces in violet light, producing distinctive emission bands that are easy to detect and measure. Almost every comet shows CN emission. It is one of the defining spectroscopic signatures of cometary activity. Except 3I/Atlas shows almost none. The CN bands are weak or absent in every spectrum. Observers search carefully using sensitive instruments and long exposures. Some spectra show marginal detections, CN emission barely above background noise, but the signal is far weaker than expected based on the comet's total outgassing rate and the brightness of other emission lines. The ratio of CN to other species is the key diagnostic. In typical solar system comets, the production rate of CN is roughly 0.5% of the water production rate. If 3I/Atlas produces water at 1027 molecules per second, it should produce CN at about 5 by 124 molecules per second. This should create easily detectable emission, but observations suggest CN production is at least 10 times lower, possibly 100 times lower. Several explanations are possible. Perhaps the comet is depleted in nitrogen-bearing organics. Perhaps the parent molecules that produce CN are different in this interstellar visitor, with photodissociation pathways that do not efficiently create CN. Perhaps nitrogen is present but locked in refractory materials that do not sublimate at the temperatures encountered in the inner solar system. Carbon and nitrogen have similar cosmic abundances. They rank 4th and 5th among the most common elements in the universe, after hydrogen, helium, and oxygen. In the interstellar medium, carbon is slightly more abundant than nitrogen by a factor of about 3. In the solar system, nitrogen is underabundant relative to carbon compared to cosmic ratios, suggesting some nitrogen was lost during solar system formation, perhaps escaping as N2 gas, which does not condense easily. If 3I/Atlas formed in a system where nitrogen loss was even more efficient, the comet might be genuinely nitrogen poor. Alternatively, if the formation temperature was very low, nitrogen might have condensed as N2 ice, molecular nitrogen, which is extremely volatile and would have sublimated during any previous warming event, leaving the comet depleted in nitrogen overall. The mystery remains unresolved. Observers continue searching for nitrogen-bearing species. Some efforts focus on detecting N22+, ionized molecular nitrogen, which produces emission in the far ultraviolet. Other observers search for ammonia, NH3, or ammonium compounds. So far, no clear detections. The comet's nitrogen budget remains uncertain, and yet this absence is itself informative. It tells us that not all comets are chemically identical. It demonstrates that formation conditions vary across different stellar systems. It suggests that the chemistry of planet formation is sensitive to local conditions, temperature, pressure, elemental abundances, radiation environment, and that these conditions were different in the system where 3I/Atlas formed. By mid-October, the comet crosses 2.3 AU inbound. Temperature reaches 167 Kelvin. The outgassing rate peaks around 1028 molecules per second, 10 billion molecules every second, total across all species. The coma diameter exceeds 100,000 kilometers. The dust tail stretches for 500,000 kilometers. A faint streak visible in long-exposure CCD images. Photometric measurements reveal periodic variations in brightness. The light curve shows a clear modulation with a period of approximately 7.3 hours. This is the rotation period of the nucleus, the time required for the irregularly shaped body to complete one full spin. As different surface areas face the Sun and Earth, the amount of reflected light changes, creating the observed brightness variation. The amplitude of the variation is about 0.15 magnitudes, suggesting the nucleus is moderately elongated, perhaps with an axis ratio around 1.5. 1. More extreme shapes would produce larger amplitude variations. The rotation appears stable. No evidence for tumbling or precession on timescales of days to weeks. The angular momentum vector points in some direction fixed in space, the body spinning around that axis like a slowly rotating football. This rotation affects the outgassing pattern. As the nucleus spins, different regions pass through the subsolar point, the location on the surface where the sun appears directly overhead and solar heating is maximum. These regions heat up, sublimation intensifies. Localized jets of gas erupt from active areas. Then rotation carries those areas into shadow. They cool. Sublimation decreases. Meanwhile, other regions rotate into sunlight and begin outgassing. The result is a time-variable coma with structure that rotates with the nucleus. High-resolution images might reveal spiraling jets or fan-shaped structures in the coma. Patterns traced by gas and dust ejected from active regions as the nucleus rotates. But 3I/Atlas is too small and distant for such detail to be resolved. The coma appears smooth and featureless in available images, any structure washed out by the limited resolution. Infrared observations measure thermal emission from the nucleus itself, radiation emitted by the warm surface in the infrared part of the spectrum. The thermal flux is very weak, requiring sensitive instruments and careful background subtraction. But by measuring the infrared brightness and comparing it to visible brightness, astronomers can estimate the nucleus size and albedo. The thermal models suggest a nucleus diameter around 400 to 500 meters, with uncertainty perhaps 50 meters in either direction. The albedo, the fraction of sunlight reflected rather than absorbed, is approximately 4 to 6%, typical for cometary nuclei, which are among the darkest objects in the solar system. Darker than coal, darker than asphalt, only slightly more reflective than lamp black. This darkness comes from the surface composition, a mixture of carbonaceous organics, silicate dust, and ice. The organics are complex, refractory materials produced by radiation processing and thermal alteration of simpler molecules. They form a dark crust on the nucleus surface, insulating the ice below, lowering the albedo, absorbing sunlight efficiently, and converting it to heat. The low albedo means the surface temperature is higher than it would be for a brighter object at the same distance. A perfectly black body would be warmest. A perfectly reflective body would stay coolest. Cometary nuclei, with albedos around 5%, fall closer to the black body limit, maximizing absorption and surface temperature. And yet, despite the dark surface, the nucleus does not retain heat efficiently. The thermal inertia, a measure of how quickly the surface temperature responds to changing illumination, appears to be low. This suggests the surface layer is porous, composed of loosely packed grains with vacuum spaces between them. Such a structure insulates poorly in the traditional sense, but also stores little heat, allowing rapid temperature changes between sunlit and shadowed regions. Low thermal inertia creates strong temperature contrasts on the nucleus. The subsolar point may reach 200 Kelvin or higher in peak sunlight. The night side may cool to 100 Kelvin or below. The average surface temperature, accounting for rotation and geometry, calculates to the equilibrium value around 165 Kelvin at 2.3 AU. But local temperatures vary widely around this average. These temperature variations drive differential sublimation. Hot spots outgas vigorously. Cold spots remain dormant. The outgassing pattern is patchy, controlled by rotation, surface topography, dust coverage. The overall sublimation rate averages out over time as the nucleus rotates. But instantaneously, the process is highly non-uniform. All of this complexity, rotation, thermal inertia, albedo, temperature distribution, differential sublimation, operates according to well-understood physics. The equations are known. The processes are predictable, and yet the details remain difficult to observe directly because the comet is small and distant, and the resolution of available instruments is limited. What can be measured is the integrated effect, the total outgassing rate, the average coma brightness, the overall spectroscopic signature. These bulk properties are accessible, and they tell the essential story. The comet crossed the boundary at 3.0 AU. The transformation began. The dormant object awakened. The process continues now, driven by rising temperature, approaching the peak that will come at perihelion. Only 60 more days until closest approach to the Sun. Only 60 more days until maximum outgassing. Maximum brightness, maximum activity, only 60 days. And then the long fade begins as the comet recedes outward. Cooling, crossing the boundary again in reverse, returning to dormancy. Departing forever into the dark. November arrives. The comet continues inward. Distance shrinks below 2.0 astronomical units. Temperature rises above 175 Kelvin. Water sublimation dominates now, exceeding carbon monoxide production for the first time. The chemical composition of the coma shifts. Hydroxyl emission, the spectroscopic signature of water photodissociation, strengthens in ultraviolet observations. The comet begins to resemble solar system comets more closely, at least in appearance, though the underlying chemistry remains distinct. Observers note increased dust production. The dust-to-gas ratio, which measures the relative mass of dust versus gas in the outflow, rises from approximately 0.3 in September to nearly 0.5 by early November. This suggests that water sublimation is more efficient at lifting dust grains from the surface than carbon monoxide was. Water molecules, being more massive than CO molecules, carry more momentum. When they sublimate and stream away from the surface, they drag dust particles along, lofting them into the coma where radiation pressure and solar wind push them into the dust tail. The dust tail grows more prominent. By mid-November, it extends over 1 million kilometers in the anti-solar direction. A faint yellowish streak visible in color images. The yellow tint comes from the dust grain properties, their size, composition, and the way they scatter sunlight. Cometary dust is a mixture of silicates and organics, grains typically 0.1 to 10 micrometers in diameter, small enough to be pushed efficiently by radiation pressure, large enough to scatter visible light. The dust grains carry their own scientific information. Their composition reflects the solid materials present in the protoplanetary disk where the comet formed: silicates, compounds of silicon, oxygen, magnesium, iron, condensed from high-temperature gas in the inner regions of the disk, or were present as pre-existing grains in the molecular cloud that collapsed to form the star and disk. Organics formed through gas phase chemistry and grain surface reactions in colder regions. If samples of the dust could be collected and analyzed, they would reveal isotopic ratios, mineralogy, organic composition, direct measurements of the alien stellar environment. But 3I/Atlas passes too far from Earth for sample collection. The closest approach to Earth is over 2 astronomical units, far beyond the range of any existing or planned sample return mission. The dust grains drift into interplanetary space, dispersing, becoming part of the general zodiacal dust cloud, their individual origins lost. Remote spectroscopy provides some information. Infrared spectra of the dust show broad emission features around 10 micrometers wavelength, characteristic of silicate grains. The exact shape and position of these features depend on grain composition. Olivine and pyroxene produce slightly different spectral signatures. Analysis suggests the dust contains both, a mixture typical of primitive solar system materials, but with abundance ratios that may differ slightly. Though uncertainties are large, polarimetry, measurement of light polarization, also provides clues about dust properties. Scattered sunlight becomes partially polarized, and the degree of polarization depends on grain size, shape, and composition. Observations in late November show polarization levels around 20% at phase angles near 90 degrees, typical for cometary dust, suggesting grain properties similar to solar system comets despite the different formation environment. This similarity is perhaps surprising, or perhaps not. The physics of dust grain formation is universal. Silicates condense from cooling gas according to thermodynamic equilibrium. Organics form through well-understood chemical pathways, unless the elemental abundances in the parent star system were radically different from solar. The dust composition should be broadly similar, only in subtle details, isotopic ratios, minor element abundances, specific organic molecules. Would the alien origin be detectable? And those subtle details remain largely inaccessible. The observations are not precise enough. The comet is not close enough. The instruments, though sophisticated, cannot extract every piece of information encoded in the faint light crossing hundreds of millions of kilometers of space. By late November, the comet crosses 1.9 AU inbound. Temperature exceeds 180 Kelvin. Peak outgassing rate reaches approximately 2 × 10^28 molecules per second. The coma diameter stabilizes around 150,000 kilometers. Further expansion is limited by photodissociation timescales and solar-wind interaction. The dust tail stretches 1.5 million kilometers, a substantial structure, though still faint. Requiring dark skies and modest telescopes to detect visually, amateur astronomers begin to photograph the comet. Equipped with CCD cameras and computerized telescope mounts, dedicated amateurs can track the slowly moving comet and integrate exposures long enough to reveal the coma and tail. The images appear on astronomy forums and websites. The comet remains far too faint for naked eye visibility, magnitude 13 or 14 at best, but it is now accessible to serious amateur equipment. Professional observations continue with higher priority. Telescope time is allocated on major instruments. Spectroscopic campaigns measure composition and outgassing rates. Photometric monitoring tracks brightness and rotation. Polarimetric observations characterize dust properties. Every observation adds data points, refines parameters, improves models, and always. The comparison to Oumuamua looms in the background. The first interstellar visitor, detected in October 2017, was profoundly different from 3I/Atlas. Oumuamua showed no detectable outgassing, no coma, no tail. It appeared asteroidal, though its motion suggested slight non-gravitational acceleration, as if some weak force was pushing it. The acceleration remained unexplained. Perhaps outgassing of volatiles too faint to detect. Perhaps radiation pressure on an unusually reflective surface. Perhaps something else. 3I/Atlas, by contrast, is unambiguously cometary. The outgassing is strong and easily measured. The coma and tail are obvious. The spectroscopic signatures are clear. There is no mystery about the nature of this object. It is a comet, behaving as comets behave, sublimating as comets sublimate, following the physics that all comets follow. And yet it came from another star, and yet it carries chemistry from another system, and yet it is only the second confirmed interstellar object, making it scientifically precious despite its apparent ordinariness. The sample size is 2. Conclusions must be cautious. But already a pattern suggests itself. Interstellar objects are diverse. They include both comets and asteroids, or at least objects that appear cometary and objects that appear asteroidal. They vary in composition, activity, trajectory. They are not a uniform population. This diversity reflects the diversity of planetary systems across the galaxy, the range of formation conditions, the variety of ejection mechanisms. Billions of planetary systems exist in the Milky Way, Each system ejects small bodies during its formation and evolution. Giant planets migrate, scattering planetesimals. Stellar encounters perturb Oort clouds. Close binary companions strip material from each other's disks. The ejection rate per system is uncertain, but models suggest every star ejects billions to trillions of small bodies over its lifetime. Multiply by hundreds of billions of stars, and the galaxy must contain a vast population of interstellar objects, rogue planets, asteroids, comets, drifting through the space between stars. Unbound to any system, traveling at galactic velocities, most will never encounter another star closely enough to be detected. Occasionally, one passes through a planetary system, warms briefly if it passes close to the star, then continues outward into darkness. We happen to live in an era when our technology can detect these passages. Sky surveys scan the heavens nightly. Automated software detects moving objects. Follow-up observations determine orbits. Within days, a newly discovered object can be recognized as interstellar based on its hyperbolic trajectory. Before 2017, no interstellar objects had been confirmed. After 2019, the detection rate will increase as surveys improve. Estimates suggest 1 or 2 detectable interstellar objects pass through the inner solar system per year. Most are not detected because they are faint, fast-moving, and present for only a brief window before departing beyond observable range. 3I/Atlas was detected because Gennady Borisov is diligent, because the comet happened to pass through a well-surveyed region of sky, because it became active, developing a coma that made it brighter and more noticeable. Because the hyperbolic orbit was calculated quickly and recognized as interstellar before the comet receded too far. Chance played a role. Timing played a role. But observation and calculation transformed chance into knowledge. And knowledge, once gained, persists. The data will outlast the comet's visibility. The spectra, images, measurements, all archived, all available for future analysis. Future reinterpretation as understanding deepens and models improve. The comet itself will fade and vanish, but the record remains. December 8, 2019. Perihelion, closest approach to the Sun. The comet reaches 2.006 astronomical units from the solar surface, nearly exactly twice the Earth-Sun distance, just inside the orbit of Mars. This is as close as it will come. This is the moment of maximum solar flux, maximum temperature, maximum outgassing. Surface temperature peaks near 185 Kelvin on the sunlit hemisphere. The subsolar point, where the Sun appears directly overhead, may reach 190 Kelvin or slightly higher. Water sublimation is vigorous. Carbon monoxide continues to sublimate as well. Though water now dominates the total production rate, the combined outgassing rate approaches 3 by 28 molecules per second, 30 billion molecules every second streaming away from the nucleus. And yet, by the standards of famous comets, this is modest. Comet Hale-Bopp, which passed perihelion in 1997, produced gas at rates exceeding 1030 molecules per second. Comet Halley, at its 1986 perihelion, produced around 1029 molecules per second. Even typical Jupiter family comets often exceed the outgassing rate of 3I/Atlas. This interstellar visitor is small and not particularly active. Its fame comes from origin, not from spectacle. The brightness peaks at magnitude 12.5, perhaps 13 depending on observing geometry and filter, visible in amateur telescopes of 6-inch aperture or larger under dark skies, photographable with modest equipment, but not a naked eye object, not a great comet in the classical sense. Most of the public never hears about it. Only astronomers and dedicated comet enthusiasts track its progress. Professional observations intensify around perihelion. This is the optimal time for detailed spectroscopy. The comet is brightest, the signal strongest, the signal-to-noise ratio most favorable. Observers want to measure everything possible before the comet begins its outbound journey and fades. A high-resolution spectra reveals subtle features. Emission lines from minor species, atomic oxygen, sodium, possibly even iron, appear weakly in some spectra. These atoms are released from dust grains heated by sunlight or sputtered by solar wind. Their presence indicates that dust composition includes these elements, as expected for silicate minerals. Isotopic measurements are attempted but prove challenging. Isotope ratios, such as deuterium to hydrogen or 13C to 12C, encode information about formation conditions and processing history. Different isotopic ratios would definitively confirm chemical differences between three I/Atlas and Solar System comets. But isotopic lines are weak, often blended with other features, requiring very high spectral resolution and signal-to-noise. Some observers report tentative detections of deuterium in water, HDO instead of H2O, suggesting a DH ratio perhaps slightly elevated compared to terrestrial water. But the error bars are large. The measurement is marginal. More data would be needed to confirm the result. And the comet is already at perihelion, about to begin fading. The nucleus continues to rotate with the same 7.3-hour period measured earlier. No evidence for changes in rotation state despite the vigorous outgassing. The outgassing produces a weak rocket effect. The momentum carried away by sublimating gas creates a tiny thrust on the nucleus. Over time, this thrust can change the comet's orbit and rotation. But for a small, weakly outgassing comet like 3 I/Atlas, the effect is minimal, barely detectable in the orbital calculations. The trajectory itself is measured with extraordinary precision. Radio telescopes detect the comet using radar. Well, attempts are made. The comet may be too distant for successful radar detection, but optical astrometry provides positions accurate to a fraction of an arcsecond. These positions, combined with earlier observations, determine the orbit to high accuracy. The orbital elements are refined. Eccentricity 3.357, perihelion distance 2.006 AU. Argument of perihelion 209 degrees. Longitude of ascending node 308 degrees. Inclination 44 degrees. The orbit is tilted significantly relative to the ecliptic plane. The comet approached from high southern ecliptic latitudes and will depart toward high northern latitudes, passing through the inner solar system at a steep angle. The incoming velocity at large distances from the Sun, the asymptotic velocity as distance approaches infinity, is 32.2 kilometers per second. The outgoing velocity will be slightly different due to the rocket effect of outgassing. The comet ejects mass, and by conservation of momentum, the nucleus gains a small velocity change. Calculations suggest the velocity change is around 10 to 20 meters per second, less than 0.1% of the total velocity, but measurable in principle if enough observations are obtained. The trajectory can be extrapolated backward and forward in time. Backward, the path traces through interstellar space, intersecting the locations of various stars as they were positioned thousands or millions of years ago. No clear candidate parent star emerges. The direction of origin points toward Cassiopeia, but no specific star in that direction appears to be the source. Forward, the path extends outward through the solar system, past the orbits of Jupiter, Saturn, Uranus, Neptune, into the Kuiper Belt and beyond, eventually leaving the Sun's gravitational influence entirely and heading back into interstellar space. The comet will cross the heliopause, the boundary between the solar wind and the interstellar medium, in a few thousand years. After that, it will be truly gone, reclaimed by the galaxy, drifting through the void until perhaps millions of years hence it encounters another star. But that future lies far ahead. For now, in December 2019, the comet is at perihelion. Bright, active, observable. Telescopes around the world gather data. Images accumulate. Spectra fill archives. The comet is studied intensely. Every piece of available information extracted. The scientific return maximized during this brief window of opportunity. And then, as December progresses, the comet begins to recede. Distance increases. Temperature drops. Outgassing decreases. The peak has passed. The transformation is about to reverse. The comet crossed the boundary at 3.0 AU inbound. Moving from dormancy to activity, it will cross the same boundary again at 3.0 AU outbound, moving from activity back to dormancy. The process is symmetric. The physics operates in both directions. Sublimation activates during approach, deactivates during recession. Only the direction of time distinguishes the two crossings. Only the accumulation of entropy, the irreversible dispersal of molecules into space, marks the difference between inbound and outbound. The trajectory is reversible. The physics is time-symmetric, but the comet loses mass with every moment of outgassing, and that mass is not recovered. By the time the comet crosses 3.0 AU outbound, it will have lost perhaps 1 million tons of material, gas and dust combined, sublimated and ejected, dispersed into the solar system. This is a tiny fraction of the total nucleus mass, perhaps 1% or less, but it is irreversible. The comet that departs is lighter than the comet that arrived, and this, too, encodes history. Every passage near a star removes material. If the comet has made previous close passages, perhaps encountering other stars during its millions of years of wandering, it may have lost significant mass over time. Perhaps it was once much larger. Perhaps the current nucleus is a remnant, depleted of volatiles, covered with an insulating crust of refractory material. Or perhaps this is its first close stellar encounter since ejection. Perhaps the ices are pristine, unprocessed, unaltered by heat since formation. The observations cannot distinguish these scenarios. The comet's history before detection remains unknown. What is known is the present. What is measured is the current state. What is recorded is this moment, this perihelion passage, this brief interval when an object from another star crosses through our system, warms briefly, outgasses, and begins its departure. The moment is fleeting. The comet is already receding, but the data will persist, archived in observatories, stored in databases, available for analysis decades or centuries hence when understanding deepens and context expands. Only took millions of years for the comet to arrive. Only took a few months to observe. Only took light speed to transmit the information from comet to telescope to detector to archive. Only took human curiosity to assign meaning to the measurements. The recession begins. Distance increases. The comet moves outward along its hyperbolic trajectory, retracing in reverse the path it followed inbound. By late December, distance exceeds 2.1 AU. Surface temperature drops below 180 Kelvin, water sublimation decreases. The outgassing rate falls. The coma begins to shrink. The process is gradual, spread over weeks and months. There is no sudden shutoff, no abrupt transition. Temperature declines smoothly with increasing distance according to the inverse square law. Sublimation rate decreases exponentially with temperature according to the Clausius-Clapeyron equation. The combined effect is a steady, predictable decline in activity. Observations continue through January 2020. The comet is still bright enough for spectroscopy, still outgassing vigorously enough to produce measurable emission lines. Hydroxyl emission persists. Carbon monoxide remains detectable. The dust tail, though fading, still extends several 100,000 kilometers. The comet is active, but declining. By February, distance reaches 2.5 AU. Temperature falls to 162 Kelvin. Water sublimation becomes weak. The hydroxyl emission fades. Carbon monoxide becomes the dominant species again. As it was during the inbound approach, the chemistry of the coma reverses, tracing backward through the sequence observed in September and October. The symmetry is not perfect. The rotation state may have changed slightly due to outgassing torques. The surface may be altered, fresh ice exposed during perihelion, dust redistributed, active areas shifted. The outgassing pattern on the outbound leg may differ slightly from the inbound pattern, but to first order, the process is reversible. Warm up, sublimate, cool down, freeze. Photometric observations show the comet fading. Magnitude increases, meaning brightness decreases, as distance grows and outgassing declines. By late February, the comet has dimmed to magnitude 15. By March, magnitude 16. The coma shrinks. The tail shortens. The comet is returning toward the dormant state in which it was first discovered, and observers know what is coming. The boundary at 3.0 AU lies ahead. When the comet crosses that distance outbound, carbon monoxide sublimation will cease. The coma will collapse. The comet will become dormant again, appearing once more as a point source in telescope images, indistinguishable from an asteroid except for its hyperbolic orbit. The outbound crossing will occur in late March or early April 2020, depending on exact trajectory details. Observers plan campaigns to document the transition, to measure the final spectra while the comet is still active, to capture the moment when outgassing stops. But then, in March 2020, something else happens. COVID-19. The pandemic, lockdowns, observatory closures, telescopes shut down, observing campaigns are cancelled. Travel restrictions prevent astronomers from reaching remote observatories. The world focuses on the crisis, and a small, faint comet receding into the outer solar system drops in priority. Some observations continue. Automated telescopes operate remotely. Amateur astronomers observe from home. But the intensive professional campaigns planned for the outbound crossing are curtailed. Data becomes sparse. Coverage becomes irregular. The comet fades and the observations dwindle. By April 2020, the comet crosses 3.0 AU outbound. Surface temperature drops to 150 Kelvin. Carbon monoxide sublimation should cease. The coma should collapse. The transformation should reverse, returning the comet to dormancy. But observations from this period are limited. A few spectra exist, showing weak carbon monoxide emission, possibly residual outgassing from subsurface ice or from the warming lag caused by thermal inertia. A few photometric points show the comet continuing to fade. But detailed, systematic observations of the outbound crossing are absent. The scientific record is incomplete. The pandemic has interrupted the observation sequence. The comet continues its journey, indifferent to human concerns, following its trajectory with mathematical precision, cooling and deactivating according to thermodynamic law. But the human record of this process is fragmentary. The documentation imperfect. This gap in the data is unfortunate, but not catastrophic. The inbound crossing was well documented. The perihelion observations were thorough. The basic physics is understood. The outbound crossing, though poorly observed, almost certainly proceeded as expected. Carbon monoxide sublimation ceased around 3.0 AU. The coma collapsed. The comet returned to dormancy. By May 2020, the comet is beyond 3.2 AU and fading towards magnitude 18. Only large professional telescopes can still detect it. The object appears point-like again. Spectroscopy is no longer feasible. The signal is too weak. Only astrometric measurements continue, tracking position to refine the orbit, monitoring the comet's slow recession. By June, magnitude 19. By July, magnitude 20. The comet is now at the limits of detection even for major observatories. A few final positions are measured. The orbit is updated one last time. And then the observations cease. The comet recedes beyond detection range, lost in the vastness of the outer solar system, invisible to even the most powerful telescopes on Earth. But it is still there, still traveling outward, still following the hyperbolic trajectory calculated from earlier observations. Distance continues to increase. 4.0 AU in mid-2020, 5.0 AU by early 2021, 10 AU by 2025, 20 AU by 2035. The comet crosses the orbit of Uranus, then Neptune, then enters the Kuiper belt, still moving at 32 kilometers per second relative to the Sun. Eventually, in a few hundred years, it will reach the scattered disk. The region beyond 50 AU where the Sun's influence weakens and orbital periods stretch to thousands of years. In a few thousand years, it will cross the heliopause at perhaps 100 to 120 AU, entering true interstellar space once more. The Sun will be just another star in the sky, bright but no longer dominant. The solar wind will fade to nothing. The comet will be alone again, and it will continue. Velocity 32 kilometers per second, 1 light year every 9,000 years. The nearest stars are several light years distant. Tens of thousands of years will pass before the comet approaches another stellar system closely enough to be warmed again. Perhaps hundreds of thousands of years, perhaps millions. Perhaps it will never encounter another star closely. Perhaps it will drift through the galaxy indefinitely, one of countless rogue objects wandering the space between systems illuminated only by starlight. Frozen at temperatures near absolute zero, inert and dormant for the rest of cosmic time. Or perhaps, millions of years hence, it will pass near another star. Perhaps that star will have planets. Perhaps one of those planets will harbor intelligent life. Perhaps observers there will detect the visitor, measure its trajectory, determine its interstellar origin, study its composition, and wonder about the distant system where it formed. Perhaps they will find chemical signatures that point back to our Sun. Perhaps isotope ratios or organic molecules will encode information about the solar nebula. Perhaps they will reconstruct the comet's journey, calculate its trajectory backward through galactic space, and identify the Sun as the star it passed in the early 21st century. Perhaps, or perhaps not. The future is uncertain, unknowable, extending across timescales that dwarf human history and human comprehension. What is certain is the past. The comet arrived. It was detected. It crossed the boundary at 3.0 AU. It warmed and outgassed. It was observed, measured, characterized. Data was gathered. Knowledge was gained. And then it receded, crossing the boundary again, returning to dormancy, departing beyond detection. The entire observable episode lasted less than 1 year, August 2019 to mid-2020. 12 months from discovery to final observation. A brief window in the comet's million-year journey. A fleeting moment in the 4.5 billion-year history of the solar system. An infinitesimal interval in the 13.8 billion-year age of the universe. And yet, in that brief window, the boundary was crossed, the transformation occurred, the physics was demonstrated, the data was recorded. The boundary itself is timeless. It exists for every comet approaching every sun-like star. It has existed since stars first formed and will exist until the last stars fade. It is a consequence of radiation, distance, and thermodynamics, mathematical relationships that do not change, physical laws that operate the same way always and everywhere, 3 astronomical units, 150 Kelvin, carbon monoxide sublimation threshold. The numbers are precise, the physics is deterministic, the boundary is real. And on 2 occasions in 2019 and 2020, a visitor from another star crossed that boundary, once inbound, once outbound, demonstrating in our own solar system the universal processes that govern cometary behavior across the galaxy. Only we were watching, only we measured, only we understood. The comet crossed the boundary without awareness, without purpose, following physics blindly. The transformation occurred automatically, molecules sublimating when temperature exceeded binding energy, consequences following from causes with mechanical inevitability. Only humans assign meaning, only humans construct narratives, only humans remember, and the memory persists in the data. In the archived spectra, showing carbon monoxide emission appearing in September and fading in April, in the light curves showing brightness increasing, then decreasing, in the orbital elements defining the hyperbolic trajectory, in the images capturing the faint coma and tail. The data is objective. The physics is universal. But the interpretation, the significance, the story, these are human constructions, ways of organizing information, frameworks for understanding. The boundary was crossed. That much is certain. The rest is commentary. 32 kilometers per second. This velocity has meaning only in context. Relative to what? Relative to the Sun. The comet's speed varies, fastest at perihelion, slowest at infinite distance. Relative to Earth, the speed changes constantly as both bodies move in their respective paths. Relative to Jupiter or Saturn or any other planet, different again. But relative to the local standard of rest, the average motion of stars in the Sun's neighborhood of the galaxy, the velocity is 32.2 kilometers per second. This is the speed at which the comet moves through galactic space when far from any star, when the Sun's gravity no longer significantly affects its motion, when it is simply another piece of cosmic debris drifting through the Milky Way. 32 kilometers per second is typical for stars in the solar neighborhood. The Sun itself moves at about 20 kilometers per second relative to the local standard of rest. Nearby stars have similar velocities, typically ranging from 10 to 50 kilometers per second. The comet's velocity is unremarkable by galactic standards. It is not an unusually fast object. It was not accelerated by any exotic process. It is simply moving at the characteristic speed of stellar motions in this part of the galaxy. This velocity was imparted during the ejection event, whenever and wherever that occurred. When the comet was flung from its home system, it inherited the orbital velocity it had around its parent star, plus whatever velocity was added by the gravitational slingshot that ejected it, minus or plus the motion of the star itself through the galaxy. The vector sum of these components determined the final velocity and direction. The exact ejection mechanism remains uncertain. Planetary migration is one possibility. When giant planets form and migrate through a protoplanetary disk, they scatter smaller bodies in all directions. Some fall inward toward the star, some are ejected outward. Computer simulations of planetary system formation show that ejection is common, perhaps inevitable. Every system with giant planets probably ejects millions or billions of small bodies during its first few 100 million years. Stellar encounters are another mechanism. If a star passes through or near another star's Oort cloud, gravitational perturbations can scatter comets onto highly eccentric orbits. Some of these orbits are unbound. The comets escape, traveling into interstellar space. This process continues throughout a star's lifetime, slowly eroding the Oort cloud, populating the galaxy with free-floating comets. Supernovae can also eject material. Though this seems unlikely for 3I/Atlas, a supernova would vaporize most nearby objects and heavily irradiate anything that survived. The comet shows no evidence of such processing. Its composition appears primitive, unaltered by extreme temperatures or radiation. More likely, the comet was ejected gently by planetary dynamics, achieving escape velocity through gravitational interactions rather than explosive events. The velocity of 32 kilometers per second is consistent with this scenario. It is fast enough to escape a typical stellar gravity well, slow enough to suggest ejection by planetary scattering rather than more violent processes. Once ejected, the comet began its journey through interstellar space. The travel time depends on the distance to the source. If the parent star is 100 light-years away, the comet has been traveling for about 900,000 years at 32 kilometers per second. If 1,000 light-years away, 9 million years. If 10,000 light-years, 90 million years. The uncertainty is large. The trajectory can be traced backward through space, but the galaxy rotates, and stars move in complex orbits around the galactic center. Reconstructing the positions of stars millions of years ago is difficult. Small errors in velocity measurements propagate into large errors in calculated origin point. The comet could have come from any of thousands of candidate systems. What is certain is that it came from elsewhere and is returning to elsewhere. The passage through the solar system is temporary. The sun's gravity bends the trajectory but cannot capture it. The comet swings past perihelion and continues outward, accelerating back toward its asymptotic velocity, heading in a new direction determined by the hyperbolic orbit geometry. The outbound trajectory points toward a different region of sky than the inbound trajectory. The comet arrived from Cassiopeia. It departs toward a point in the sky perhaps 90 degrees away, the exact direction depending on orbital parameters. The deflection is substantial. The sun's gravity significantly changed the comet's direction, even though it could not change the speed by much. In galactic coordinates, the inbound velocity vector and outbound velocity vector differ by tens of degrees. The comet's path through the galaxy has been permanently altered by the solar encounter. It will never return to this region of space. It will never pass near the sun again. The trajectory is open, the future path unknown, but certain to be far from here. As the comet recedes, it carries with it the chemical signature of the solar encounter. The surface has been altered by solar heating. Some volatiles have been lost. The outer layers have been processed by ultraviolet radiation. Cosmic rays will continue to bombard the surface during the long journey ahead, modifying chemistry, creating new compounds, darkening the surface further. If the comet ever encounters another star closely enough to warm again, observers there might detect these alterations. They might measure isotope ratios that suggest processing by a G-type star. They might find organic molecules produced by ultraviolet photolysis at specific wavelengths characteristic of solar radiation. The comet would carry evidence of its visit here, readable to those who know what to look for, but such evidence would be subtle, easily overlooked, perhaps indistinguishable from the comet's native composition, and the probability of another close stellar encounter is low. The galaxy is vast. Stars are separated by light years. The comet could wander for billions of years without passing near another star. More likely, it will drift through interstellar space indefinitely, slowly accumulating cosmic ray damage, slowly losing the most volatile ices to residual sublimation driven by starlight, slowly becoming more asteroid-like as the ice fraction decreases. Over billions of years, the comet might be transformed into a dark, nearly inert body, its cometary nature no longer obvious to a casual observer. Or perhaps it will fall into a molecular cloud, a dense region of gas and dust where new stars are forming. The cloud's gravity might capture the comet, or at least slow it, bringing it into orbit around a newly forming star. The comet might be incorporated into a new planetary system, becoming a part of that system's Oort cloud or Kuiper belt, indistinguishable from native objects. Or perhaps it will survive until the far future. until the last stars have faded, until the galaxy is dark and cold, populated only by brown dwarfs and black holes and stellar remnants. The comet would persist as a relic of an earlier era, a frozen time capsule from the age of star formation, drifting through an empty cosmos, unobserved and unobservable. These futures are speculative. The comet's actual fate is unknowable. Prediction over millions or billions of years is impossible. Too many contingencies, too many potential interactions, too much chaos in the gravitational dynamics of a galaxy containing hundreds of billions of stars. What is known is the present trajectory, the velocity, the direction, the orbit. These can be calculated precisely from the observations made in 2019 and 2020. The path for the next few thousand years is determined. Beyond that, uncertainty grows, but the general picture remains. The comet departs, accelerates outward, crosses into interstellar space, and continues traveling through the galaxy at 32 kilometers per second until something else happens. And that velocity, 32 kilometers per second, remains constant, or nearly so. Small perturbations from distant stars might change it by a few meters per second per million years. Galactic tides might alter the trajectory slightly, but absent a close encounter with another star or a passage through a dense molecular cloud, the velocity persists. Only the speed imparted billions of years ago during formation and ejection, conserved through the long journey, unchanging across light years, carrying the comet ever onward through the void. Only motion without destination, only velocity without purpose, only physics, operating as it always has, indifferent to meaning or outcome. The comet recedes at 32 kilometers per second, and the number itself is all the explanation needed. The boundary taught us what we already knew. Sublimation thresholds are not new science. The relationship between distance, temperature, and volatile behavior has been understood for decades. Textbooks describe it, models predict it, observations of solar system comets confirm it repeatedly. The physics is well established, and yet, observing the process in an interstellar comet adds something, not new physics, but new context, confirmation that the principles apply universally, not just to objects formed in our solar system. Validation that cometary science developed from studying solar system objects extends to visitors from other stars. This might seem obvious. Physical laws are supposed to be universal. The same equations should apply everywhere. But science advances by testing assumptions, by extending theories into new regimes, by checking whether predictions hold in circumstances different from those where the theories were developed. 3I/Atlas provided such a test. A comet from another stellar system, formed under different conditions, composed of ices condensed in an alien protoplanetary disk, nevertheless behaved exactly as cometary physics predicts, the boundary at 3. 0 AU for carbon monoxide activation was not unique to solar system comets. It applied equally to this interstellar visitor. The temperature threshold of 150 Kelvin was the same. The sublimation physics was the same. The coma formation, the tail development, the spectroscopic signatures, all matched expectations based on solar system comets. The differences were in composition, not in behavior. The chemistry was different, but the physics was identical. This is reassuring. It suggests that our understanding of comets is robust, that the models are reliable, that predictions can be trusted even for objects we have never encountered before. It increases confidence in applying cometary science to observations of exoplanetary systems, to models of planet formation around other stars, to interpretations of debris disks and asteroid belts in distant systems. If comets everywhere behave the same way, then cometary processes contribute similarly to planet formation everywhere. The delivery of water and organics to inner planets by comets, a process thought to be important for Earth's oceans and perhaps for the origin of life, likely operates in other systems as well. The role of comets in planetary system architecture, in scattering dynamics, in the delivery of volatiles, should be broadly similar across different stellar environments. The boundary also taught us about the specific composition of 3Y/Atlas by observing when the comet activated, what molecules appeared first, how the activity evolved with distance. Astronomers could infer the volatile inventory, carbon monoxide rich, water poor compared to solar system comets, nitrogen depleted or at least depleted in volatile nitrogen species. These compositional differences point to formation in a colder region than typical solar system comets, or around a cooler star, or in a disk with different elemental abundances. Each interstellar object adds one data point to the population statistics. Oumuamua was asteroid-like, or at least showed no detectable outgassing. 3I/Atlas was cometary, co-rich, weakly active, two objects, two very different compositions and behaviors. The sample is tiny, but already it suggests diversity. Future detections will expand the sample. The Vera C. Rubin Observatory, which began operations in the early 2020s, is expected to detect dozens of interstellar objects per year. Other sky surveys will contribute additional discoveries. Within a decade or two, the sample size could reach hundreds. Statistical patterns will emerge. Compositional trends will become apparent. The distribution of interstellar object properties will constrain models of planetary system formation and evolution across the galaxy, and each object that shows cometary activity will cross the same boundaries. Carbon monoxide activation around 3.0 AU for G-type stars, water activation around 2.5 AU, other volatiles at other distances. The thresholds will be observed repeatedly, confirming the physics, refining the temperature calibrations, testing the models. The boundary is reproducible. It is predictable. It is universal. These qualities make it scientifically valuable. Phenomena that occur only once or unpredictably are difficult to study. Phenomena that repeat, that follow regular patterns, that can be anticipated and observed systematically. These are the foundations of scientific understanding. 3I/Atlas crossed the boundary twice, once inbound and once outbound. The inbound crossing was well observed. The outbound crossing less so, due to the pandemic and the comet's fading, but the symmetry is expected. The physics operates in both directions. Cooling should deactivate the comet just as warming activated it. If another interstellar comet is detected early enough in its inbound trajectory, before it crosses 3.0 AW, observers might monitor the activation in detail. Spectroscopy could track the first appearance of carbon monoxide emission. Photometry could measure the brightness increase as the coma forms. Imaging could capture the development of the tail. The transformation could be documented from dormancy to full activity day by day, providing a complete observational record of the crossing. Similarly, if observations continue through the outbound journey, the deactivation could be monitored. The coma collapse could be measured. The final carbon monoxide emissions could be detected. The return to dormancy could be confirmed. The full cycle, activation, peak, deactivation, would be documented, providing a complete picture of how interstellar comets respond to solar heating. Such observations would test models of cometary behavior in detail. They would constrain parameters like thermal inertia, dust coverage, sublimation rates, coma expansion velocities. They would reveal whether interstellar comets behave identically to solar system comets or show subtle differences due to composition or structure. The boundary itself would be probed. Is 3.0 AU exact, or does it vary slightly from comet to comet depending on rotation rate, shape, surface properties? Is the activation gradual or sudden? Does it occur simultaneously across the whole nucleus, or start in localized regions and spread? These questions can be answered with sufficient observations, and the answers would refine understanding, not change the basic physics. Sublimation will always occur when temperature exceeds the threshold, but add detail, improve models, increase predictive power. This is how science advances. Observations test predictions. Results refine theories. New observations test the refined theories. The cycle continues, each iteration increasing precision, expanding scope, deepening understanding. 3I/Atlas provided one iteration, its passage through the solar system, its crossing of the boundary, its activation and deactivation, all contributed data. The data was analyzed, compared to models, interpreted, knowledge increased. The comet itself is now beyond reach, receding into interstellar space, never to be observed again from Earth. But the data remains. The spectra are archived, the images are stored, the measurements are published. Future scientists will revisit this data, reanalyze it with better models, extract additional information as understanding improves. The boundary will be studied again in future interstellar comets. The threshold will be crossed again, observed again, measured again. Each time, the physics will be confirmed. Each time, the universality of cometary behavior will be demonstrated. And each time, the simple fact will be reinforced. Temperature determines phase. Distance determines temperature. Proximity to a star determines distance. The chain of causation is clear. Deterministic, universal, only 3 astronomical units from a sun-like star, only 150 Kelvin at the surface, only enough warmth to break the weakest molecular bonds, only took the universe billions of years to create stars and planets and comets, only took humanity centuries to develop the physics to understand them, only took one interstellar visitor to demonstrate that the understanding applies everywhere. The origin remains unknown. Cassiopeia is a direction, not a destination. The constellation contains hundreds of visible stars and thousands more too faint for naked eye observation. Beyond them, millions of stars populate that region of the galaxy, extending across kiloparsecs. The comet came from somewhere in that vast volume of space, but precisely where cannot be determined. Trajectory reconstruction attempts to narrow the possibilities. By measuring the comet's velocity and position precisely, astronomers can calculate its path backward through time. In principle, this should point to the source. In practice, uncertainties accumulate. Small errors in velocity measurement propagate into large errors in position over millions of years. Galactic rotation complicates the calculation. Stars move in their orbits around the galactic center, and their positions millions of years ago were different from their positions today. Some studies have attempted to identify candidate parent stars. They search catalogs for stars in the general direction of the inbound trajectory, moving with velocities that could bring them close to the comet's past trajectory. Several candidates emerge: red dwarfs, sun-like stars, binary systems, but none can be confirmed. The uncertainties are too large. The comet could have come from any of them, or from none of them, or from a star not in the catalogs. The distance to the source is unknown. If the parent star is 100 light-years away, the ejection occurred roughly 1 million years ago. If 1,000 light-years away, 10 million years ago. If farther still, the ejection could date back tens of millions of years, to a time when Earth's continents were in different positions, when different species dominated the biosphere, when the solar system itself was in a different location in its galactic orbit. The comet carries no record of its journey. Ice remembers nothing. The molecular structure of frozen carbon monoxide or water does not encode information about time or distance traveled. Cosmic ray exposure might provide some constraint. The longer the journey, the more radiation damage accumulates. But measuring this requires detailed analysis of surface samples. which are not available. So, the origin remains a mystery. An unknown star in an unknown system ejected this comet at an unknown time. The comet wandered through interstellar space for an unknown duration before encountering the Sun. Everything about its history before August 2019 is speculation. What happens after the comet departs is equally uncertain. The outbound trajectory can be calculated, but only for the near future. Where will the comet be in 1 million years? Somewhere in that direction. At 32 kilometers per second, but the exact location depends on gravitational perturbations from stars it might pass, on interactions with molecular clouds, on encounters with other interstellar objects, none of which can be predicted. Will it ever encounter another star closely? Probably not. The galaxy is mostly empty space. Stars are separated by light years. The probability of a close encounter, close enough to warm the comet significantly, is low. Most interstellar objects wander indefinitely without ever being captured or significantly perturbed. Will it survive billions of years? Perhaps. Comets are stable in interstellar space, cold, dark, unperturbed by radiation or heat. They can persist indefinitely. Unless the comet collides with something, unlikely but not impossible, or falls into a star or black hole, also unlikely, it should survive as a frozen relic, essentially unchanged, for the rest of cosmic time. The Milky Way galaxy contains perhaps 400 billion stars. If each star ejects a billion comets during its formation and evolution, the total interstellar comet population could be 1020 or more. Most of these comets are invisible, undetected, drifting through the dark between stars. They constitute a vast, hidden population of small bodies, remnants of planetary system formation, scattered throughout the galaxy. 3I/Atlas is one of these objects. It is not unique, it is not special except in that we happen to detect it. Countless similar objects must pass through the solar system unnoticed, too faint, too fast, arriving and departing beyond detection range before any telescope can observe them. The detection of 3I/Atlas was fortunate. The comet became bright enough to notice because it developed a coma. If it had remained dormant throughout its passage, if it had passed outside 3.0 AU and never crossed the activation threshold, it might have gone undetected despite crossing through well-surveyed regions of sky. The coma made it visible. The boundary crossing saved it from obscurity, and obscurity is the fate of most interstellar objects. They pass through, invisible, unrecorded, contributing nothing to human knowledge because no one knows they exist. Only a tiny fraction of the total population is ever detected. Only a tiny fraction of detections is studied in detail. Only a tiny fraction of those studies produces significant scientific results. 3I/Atlas falls into this last category. It was detected, studied, and produced valuable data. The observations are published. The results are incorporated into models and catalogs. Future studies of interstellar objects will reference this one. Comparing compositions, trajectories, behaviors, the comet has become part of the scientific record. It has contributed to human understanding of the galaxy, of comets, of planetary system formation. Its brief passage through the observable solar system, lasting less than a year, generated knowledge that will persist as long as the data is preserved, and preservation is likely. Digital archives are robust. Backup copies exist in multiple locations. The spectra, images, orbital elements, all are stored redundantly. Even if some archives are lost, others will survive. The information will persist for decades, centuries, perhaps longer. Longer than the comet will be observable. Longer than human civilization might last. Longer, possibly, than the current configuration of the solar system, which will be disrupted billions of years hence when the sun becomes a red giant and the inner planets are destroyed. Data, once recorded, takes on a persistence that the objects it describes lack. The comet will depart and never return. The data will remain, a frozen record of a moment in time, a specific configuration of matter and energy, preserved in digital form long after the configuration itself has dispersed. This is the strange immortality of scientific observation. Events are ephemeral, objects are transient, but measurements, encoded in stable media, can outlast the phenomena they measure. The light from the comet has long since dissipated. The molecules it shed have dispersed into the solar wind. The nucleus itself recedes beyond visibility. But the spectrum captured on September 15, 2019 remains. Pixel values in a FITS file, numbers in a database, recoverable and analyzable as long as the storage medium survives. The comet came from somewhere unknown. It will depart to somewhere unknown. Only the brief middle section of its trajectory intersected with human awareness. Only during that intersection was information captured. And that information is all that remains to us. Traces of light, patterns in data, numbers in tables. The rest is inference. The origin is inferred from trajectory. The composition is inferred from spectra. The size is inferred from brightness and thermal emission. Even the existence of the boundary crossing, the moment when the comet transitioned from dormant to active, is inferred from changes in spectroscopic signatures and coma brightness. We did not see the sublimation directly. We did not watch molecules leave the surface. We saw photons, interpreted patterns, constructed models, and inferred processes. The boundary crossing is a theoretical construct supported by observational evidence, not a directly observed event. And yet, the inference is sound. The evidence is strong. The model is well tested. The conclusion is robust. The comet crossed the boundary. Sublimation began. The transformation occurred. These statements are as certain as any scientific claim can be. Only we will never see that comet again. Only the data remains. Only the knowledge persists. And the comet continues outward, silent and cold, carrying its mysteries into the dark. The archive holds everything. Every spectrum taken of 3I/Atlas, every photometric measurement, every astrometric position, stored in databases distributed across the world. The European Southern Observatory Archive contains observations from the Very Large Telescope. The Keck Observatory Archive holds high-resolution spectra. The Hubble Space Telescope Archive preserves ultraviolet images and spectra. Smaller observatories and amateur astronomers have uploaded data to the Minor Planet Center and other clearinghouses. The total volume of data is modest by modern standards. Perhaps a few gigabytes, spectral FITS files, photometric tables, astrometric reports. Not the terabytes generated by some astronomical surveys, but substantial enough to require organization, curation, preservation. The data is tagged with metadata, observation date, telescope, instrument, exposure time, filters, wavelength range. Search queries can retrieve specific observations or entire data sets. Anyone with internet access can download this data. No special permission is required. Scientific data from most observatories is public, released immediately or after a proprietary period of typically 1 year. The observations of 3I/Atlas are available to researchers, students, amateurs, anyone curious enough to look, and people do look. Years after the comet has faded from view, researchers still analyze the archived data. New techniques are applied. Better calibrations improve the measurements. Comparisons with other interstellar objects provide context. Each reanalysis might extract slightly more information, refine parameters, test hypotheses. The data is finite, but the questions that can be asked of it are not. Was there methane in the coma? The spectral resolution might not have been sufficient to detect it initially, but improved analysis methods might reveal weak signatures. Did the rotation period change during perihelion passage? Re-examining the photometric light curves with more sophisticated models might detect subtle variations. Was there spatial structure in the coma? Reprocessing images with modern deconvolution algorithms might reveal features not apparent in the original analysis. Science advances not only by collecting new data, but by extracting more information from existing data. Archival research is valuable. Old observations can answer new questions. Data collected for one purpose can be repurposed for another. The archive is a resource, not just a repository. For 3I/Atlas, the archive preserves a moment in time, September 2019 through mid-2020. A few months of observations, a visitor from another star passing through, warming, outgassing, then fading. The data captures this passage in numbers and images, a digital record of a physical event. And the physical event is gone. The comet is beyond detection, receding outward at 32 kilometers per second, now tens of astronomical units from the sun, cold and dormant again. Invisible. The coma has collapsed. The tail has dispersed. The nucleus continues alone. A dark fragment of ice and rock tumbling through space, no longer distinguishable from the countless other small bodies drifting through the outer solar system and beyond. But the data remains. The spectral lines that revealed carbon monoxide emission, the photometric points that tracked brightness changes, the astrometric positions that defined the hyperbolic orbit, all preserved, all accessible, all permanent in a way the comet itself is not. This permanence is contingent. Of course, digital storage media decay, formats become obsolete, institutions close, funding ends. Archives require maintenance, curation, migration to new media and new formats. Without active preservation, data degrades and is lost. But astronomical data is generally well preserved. The value is recognized. Efforts are made to maintain archives to ensure long-term accessibility. The data from 3I/Atlas will likely survive for decades, probably longer. Future astronomers will have access to these observations, will be able to revisit them, will incorporate them into broader studies of interstellar objects and cometary physics, and, perhaps, someday, a connection will be made. Perhaps another interstellar object will be detected with nearly identical composition, the same high carbon monoxide ratio, the same nitrogen depletion, the same spectroscopic signatures. Perhaps detailed comparison will suggest they came from the same planetary system, ejected at different times but sharing a common origin, or perhaps observations of an exoplanetary system will reveal a debris disk with chemical composition matching 3I/Atlas, suggesting that system as the source. If the distance and direction match, if the ejection age calculates correctly, if the evidence aligns, a tentative identification might be possible. Such connections are speculative, unlikely, but not impossible. The archive makes them possible. Without the preserved data, such comparisons could not be made. The comet would be forgotten, its passage unrecorded, its chemical signature lost to time. Instead, the information persists. The measurements wait in the archive, ready to be retrieved, compared, reanalyzed. The comet itself continues its journey into obscurity, but the knowledge it provided remains accessible, a permanent contribution to science. And this is the function of archives, to preserve past observations, to make them available for future research, to ensure that effort expended in collecting data is not wasted, that discoveries made can be built upon, that understanding accumulates rather than being lost and rediscovered repeatedly. The archive is memory, not biological memory, which fades and distorts, not cultural memory, which shifts and rewrites itself, but precise, quantitative memory, numbers stored exactly, images preserved pixel perfect, metadata recorded rigorously. The archive remembers what happened, when, and how it was measured. For 3 I/Atlas, the archive remembers the boundary crossing, the transition from dormant to active, recorded in spectroscopic data from September 2019. The peak activity at perihelion in December, preserved in photometric measurements and thermal observations. The outbound fading in early 2020, documented in the final astrometric positions before the comet became too faint to detect. The narrative is recorded in data. The story is told in numbers. The meaning is encoded in measurements. And anyone who knows how to read the archive can reconstruct what happened, can see the carbon monoxide emission appear, can watch the brightness increase, can calculate the temperature at which sublimation began. The boundary was crossed. The data proves it. The archive preserves the proof. And somewhere, far beyond the orbit of Neptune, beyond the Kuiper belt, beyond the heliopause, the comet continues outward, silent now, cold, dormant, exactly as it was before it encountered the sun, exactly as it will remain for millions of years, until perhaps it encounters another star and the cycle repeats. The comet does not remember the crossing. Ice has no memory. The molecular lattice does not store information about past temperatures or past sublimation. The surface has been altered, some ice lost, some dust redistributed, but these changes record nothing meaningful. They are simply consequences, not memories. Only the archive remembers. Only the data encodes what happened. Only human observers, reviewing the spectroscopic files, can reconstruct the moment when temperature crossed 150 Kelvin and carbon monoxide began to sublimate. The comet is indifferent. It followed its trajectory, obeyed physics, warmed and cooled according to distance from the sun. No awareness, no purpose, no significance beyond what observers assign, and observers assigned significance. The crossing of the boundary was noted, measured, analyzed, published. Papers were written. Conferences presented findings. The scientific community incorporated the observations into its collective understanding. The comet became a data point, a case study, an example. This is what makes the event meaningful in human terms. Not the physics itself. The universe is full of comets crossing temperature thresholds around billions of stars. Events occurring continuously throughout the galaxy, unobserved and unremarked. But this particular crossing, at this particular time, happened to intersect with human capability to observe and measure. The intersection was brief. August 2019 to mid-2020. Less than 1 year. A tiny fraction of the comet's journey. A moment in cosmic time. But during that moment, information flowed from comet to telescope to detector to archive to human understanding. The flow has stopped now. The comet is too distant, too faint. No new observations are possible with current technology. The information stream ended in 2020 and will not resume. What has been recorded is all that will be recorded from this particular visitor. But the archive endures. The data persists. The information remains accessible. And in this persistence, the ephemeral becomes permanent. The fleeting passage of an interstellar comet, observable for mere months, generates knowledge that lasts far longer. Years will pass, decades. The comet will recede to hundreds of AU, thousands of AU, eventually leaving the solar system entirely and returning to interstellar space. It will be gone, irretrievably, never to return, lost to observation forever. But the archive will still hold the spectra, the carbon monoxide emission lines from September 2019, the hydroxyl radicals from December, the photometric light curve showing the 7.3-hour rotation, the orbital elements defining the hyperbolic trajectory, all preserved, all retrievable, all analyzable by anyone who wishes to examine them. This is the strange asymmetry of astronomical observation. The events are transient. The records are durable. the phenomena disappear. The data remains, and from the data, stories can be reconstructed, narratives can be built, understanding can be derived, the boundary crossing can be inferred, visualized, comprehended, not from direct experience, which is impossible, but from the traces left in light, captured and preserved. The archive is full of such traces, spectra from thousands of comets, light curves from millions of asteroids, images of billions of stars. Each dataset preserves some event, some configuration, some moment in cosmic history. Taken together, they form a vast library of the universe's behavior, a record of processes operating across space and time. 3I/Atlas occupies a small section in this library, a few gigabytes among petabytes, a handful of observations among billions. But those observations are unique. Only one interstellar comet has had its activation boundary crossing documented in detail. Only 3I/Atlas provided that data. Future interstellar comets will add to the record. More observations will accumulate. The sample size will grow, patterns will emerge from statistics, but each individual object contributes something specific, something that cannot be extracted from the aggregate alone. 3I/Atlas contributed its composition: carbon monoxide rich, nitrogen poor, weakly active, its rotation period, its thermal properties, its response to solar heating. These specific measurements, from this specific object, add nuance that averages and trends cannot capture. And the boundary crossing, the moment when dormancy gave way to activity, was captured with precision. The distance, 3.0 AU. The temperature, 150 Kelvin. The result, carbon monoxide sublimation. The physics, universal. The data confirms what theory predicted. The observation validates the model. The measurement supports the understanding. This is the scientific method operating as designed, hypothesis tested against evidence. Prediction compared to observation. Theory refined by data. And the archive preserves both the evidence and the interpretation. Not just raw numbers, but also published papers explaining what the numbers mean. The full context is recorded. Future researchers can examine not only what was measured, but also how it was interpreted, what conclusions were drawn, what questions remained unanswered. The unanswered questions persist. Where did the comet come from? What is its exact nitrogen inventory? Did the surface composition change during perihelion passage? How long has it been traveling through interstellar space? These questions cannot be answered with available data. They remain open, awaiting future observations of other interstellar objects, or new analysis techniques, or theoretical advances, but the questions are preserved along with the data. The archive records not only what is known, but also what is unknown. The gaps in knowledge are documented as carefully as the knowledge itself. This honesty, this acknowledgement of uncertainty, is essential to science. The boundary crossing is certain. The composition measurements are certain within their error bars. The trajectory is known precisely, but the origin, the age, the future, these remain uncertain. And the archive faithfully records this uncertainty, and so the record is complete, in its way. Not complete in the sense of answering every question, but complete in the sense of capturing what was observed and what was inferred and what remains mysterious. The archive tells the truth. A visitor came, crossed the boundary, was observed, and departed. Where it came from and where it goes remain unknown. But the crossing itself is documented beyond doubt. The comet is gone now. The observations have ended. The data is final, but the archive endures, and within it, the thin boundary where 3I/Atlas change behavior is preserved forever, or at least for as long as human civilization maintains its records, keeps its archives, remembers what was seen in those months when a traveler from another star passed briefly through our sky, warmed by our sun, and showed us once again that physics operates the same way everywhere, that the universe follows consistent rules, that knowledge gained here applies there. Wherever there might be, the boundary was crossed, the data was recorded, the knowledge persists, and that persistence, that preservation, that archive, this is what remains when the comet itself has vanished into the dark. The archive is quiet now. The files rest in servers, undisturbed except when called upon. The spectra wait, pixel values unchanged, ready to be displayed whenever someone queries the database. The images sit dormant, like the comet itself in those early weeks of August, before the warming, before the transformation, somewhere beyond Neptune's orbit, beyond the scattered disk, beyond the heliopause. The actual nucleus continues, dark, cold, tumbling slowly in its 7.3-hour rotation. Though no one watches anymore, the surface is frozen solid again. All the carbon monoxide that was going to sublimate has sublimated. What remains is locked in ice, stable at these temperatures, safe from the sun's distant warmth. The comet will not cross another boundary for a very long time, perhaps millions of years, perhaps never. The galaxy is vast, and stars are far apart, and the probability of another close encounter is vanishingly small. More likely, the comet will drift through the cold dark indefinitely, unchanged, unwarmed, dormant forever. But it crossed once, at 3.0 astronomical units. In September 2019, the temperature threshold was reached. The ice began to sublimate. The transformation occurred, and we were there to see it, or rather, to measure the light, to capture the photons, to record the evidence. The evidence rests now in the archive, silent, permanent, a memory preserved in silicon and electromagnetic fields, numbers that encode a moment when an object from elsewhere briefly came alive, briefly glowed, briefly left traces in our instruments before departing back to the silence from which it came. The comet does not remember. The ice does not record. Only the archive holds the memory, and only as long as the servers run, as long as the data is maintained, as long as someone, somewhere, cares enough to preserve what was seen. And perhaps that is enough. Perhaps that is all that can be asked. The universe generates events continuously, transformations and crossings and changes occurring everywhere, always, most of them unobserved. This one was observed. This one was measured. This one left a trace. The boundary is crossed. The data is stored. The comet recedes, silent and cold, into distances we cannot follow and will never see again. And here, in the archive, in the quiet rows of numbers, the crossing is preserved, the moment endures, the boundary remains. Sleep well.